you've already practiced. Can you hear me?
Yes, we can.
I hope you had a good day and you practiced what Dr. Helen left an assignment with you. And I would like to know whether there is somebody ready to help us and go through the assignment so that we can see that whatever knowledge we are passing on, you're able to apply it on your role and also use it in your research. We are so grateful that you've again logged in after all those many days. Apparently, we don't have any noise in the background. You're not clear. There's an echo. There's no echo. You don't have anybody talking in the background. But I hope now it is clear. Okay. So we do not have any new material today. Dr. Helen has already updated the Google link with the data sets that we are going to use today. Now, we will take off like 4 minutes for you to make sure you have all the data and the script that we are going to use today. Today, Helen will finish model building and then is going to also go on to do Chi-square, logistic regression, and log linear regression. Okay? Thank you very much. And I now hand over to Helen. Okay.
Okay, thank you, Prof. Professor Susan. A very good morning to everyone, depending on where you are. In Uganda, it's still morning. It is 10:03. So from where we stopped yesterday, we want to proceed, but I would like to inquire if there is somebody who managed to do the assignment such that he or she can share with us, and then we dive into what we are supposed to do today. Anyone who managed to do the assignment can share. Yes. I don't know whether Martin is on to help us. Dr. Runyararo, kindly allow participants to share, give them rights to share their work and see how they got on with the concepts.
I see Harriet now. Something.
Dr. Runyararo, please.
Yes, I have sent Harriet to be a panelist, so she should be joining and be able to share.
We can't hear you. Am I the only one who is not hearing?
Good morning. Good morning, ladies and gentlemen. Can you hear me?
Yes, we can hear you.
Yes, I tried to do the assignment and let me try to share.
How come I can't hear anything?
Can you hear me?
I can hear you, but I think Dr. Namaweje is having problem with the computer.
Okay.
Maybe Professor Susan can help her.
It's now clear. We can hear you.
You can hear me? Eh?
Please
Yes.
go ahead.
Okay, this is the assignment we are given, and it was about considering an example on seed segregation with respect to color and shape. So I wanted to know if shape has a relationship with color. And we had two colors, yellow and green, and two shapes, round and wrinkled. The hypothesis was the color of the seed is independent of the shape, that is HO. Then HA was the color of the seed is not independent of the shape. And the chi-square value, this was part of the answer. These were the solutions to the answer. So I went ahead and restated the hypothesis, and that was step 1 of the solution. Then step 2, we had this table. we had observed values. This is according to the question, the yellow and the green, then the round and the record with respect to rows and then columns. So we had to get the summation of the rows, that is 315 and 108, to get 423, that is row 1. Then row 2, we had to get 101 plus 32 to get 133. Then with respect to columns, that is color, we had to get 315 plus 101 to get 416. Then we had to get a summation of 108 plus 32 to get 140. And the total is with respect to this 416 plus 140 to get 556. Then with respect to the column, it is 423 plus 133 to get 556. So these were the total number of observations. And then after getting the total number of observations, I went ahead to compute the expected frequencies, that is E, and the test statistic contributors. So I wrote this in the table, and this O1 is part of the question. These are the values that were given, and how I computed E1. I had to get this because according to this equation, this is the equation, row I total times column J total over total number of observations. So what I did, I had to get R1, for example, row 1 total. With this, if I wanted to get the expectation, expected frequency for yellow 1, I mean for yellow, I had to get the row 1, the total 423, and then by the column 1, that is 416, and the formula is here. 423 times 416 brackets divided by the total number of observations, and I got 316.489. Then to get went ahead to look for the expected value for the green color. I had to again use this computation, the 423, the row 1 total times the 140 for the column 2. So I have 423 by 140 in brackets over the total number of observations, and I got 106.511. Okay. And the requirement is we could get a total to confirm, because the expected frequencies that should be equal to the observed frequencies. And when I added these two, 316.489 to 106.511, I got 423, which is similar to this. And let me first finish up this, then I'll go back to look for the test statistic contributors. So when you come to this value here, how we got the expected value E2, expected observations, I went ahead to use row 2, that is 133, but times 416, according to this formula, over 556. I got 99.511. Now to get the expected value E2 for green color, I got 133 by 140 divided by 556, I got 33.489. So when I sum them up, I got the same total, which is equal to the one for the observed frequencies. Then from there, I had to go back and look for the test statistic contributors, whereby this is the formula. For example, for this yellow, it is O1 minus E1 squared over E1. Okay, so I have this 315, okay, minus this one 316. Unfortunately, I forgot to put the formula there, but it's this 315 minus 316.48 divided by 316.489. I got 0.007. I did the same here. I have 108 minus 106.511 squared according to this equation, divided by 106.511 squared. I got 0.021. I went ahead to do the same for this particular row. 101 minus 99.511 squared over 99.511 squared. I got 0.022. I did the same here. Then finally, the third step was to determine the chi-square value that whereby I got a summation of this plus this plus this, that is 0.007 plus 0.021 plus 0.022 plus 0.066, which I included in this equation that were given, okay? And I got 0.116. So the fourth step was to compute the degrees of freedom. And this is the equation R minus 1 into C minus 1. And from our question, we have two rows, that is one, this is one row, and then this is the second row. And then we have two columns, this is one column, and then this is the second column. So basically we have two rows and then two columns. So I use this equation to get 1 degree of freedom. Then I went ahead to determine the test value, the chi-square value according to the new Cambridge statistical tables. And with respect to, because I got a degree of freedom of 1, and the significance level, this is our determinant. We have 0.05, and and from this table 8 of this statistical tables, I obtained 3.481. And I said, hence we accept H naught since this value, the tabulated value, is greater than the computed value of 0.116. Then I also tried the 1% significance level, and I got 6.635 again from this table. So I said I still accept H naught because 6.635 is greater than 0.116. And then I said, therefore, the test is not significant, and we conclude that there is no strong evidence that the color of the seed is independent. Thank you very much.
Thank you so much, Harriet. Kindly come again on the conclusion.
On the conclusion, since my tabulated value was higher than the computed value of 0.116, because the hypothesis was saying H naught, the color of the seed is independent of the shape. And then HA, the color of the seed is not independent of the shape. So since my tabulated value of 3.4 something was greater than the calculated value of the chi-square value of 0.116, I accepted the hypothesis H naught and said the color of the seed is independent of the shape. Okay. That was my conclusion.
Yes, that's what I wanted to hear very well. Thank you so much. Yeah, it has been a great presentation, and I'm so excited that you've taken us from all the steps, which is very good, such that everyone is able to follow, and how you came up with the conclusion. That's a good spirit, and it enables us to see that you people are understanding what we are teaching. Good teacher. Somebody has commented that. Thank you, Harriet, for the great work done. Do we have somebody else, or what Harriet had discussed is enough? Let me say from the chat. Anyone who is willing to share? If you have if you have something different from what Harriet has shared, you can also be promoted. If there isn't, then we can move on. Okay. Somebody says it's enough and it's a good recap. Well, that's great. Okay, let's proceed. Thank you once again, Harriet, for taking us through step by step, how you set the different hypotheses and then come up with the come up with the expected frequency. How do you use the chi-square test, that is our test statistics, and then from coming up with the right conclusion, because it is always important that you set the right hypothesis. At the same time, you're supposed to come up with the right conclusion. So we are going to proceed. We've gotten a very good recap. So what we are going to do, we are going to proceed from where we stopped. And then I finished the part of categorical. We see how we do it in R, and then we'll move on to the GLM, but particularly, if time allows, we'll look at logistic regression and then Poisson regression. All right. Sorry. Okay. So this is where we ended yesterday. Let's continue. I don't know if time allows, we'll do that. So we finished that. So we are moving on to, we're looking at different where you can use the chi-square. First, we saw that in the, what Harriet has presented. Now, next, you can as well apply the chi-square in case you want to test the goodness of fit. Okay, remember, in this particular case, we are using hypothesized proportions given by another hypothesis fit for the data. So, for example, how do we test for the goodness of fit? What happened is that let's take first the theory bit and then see how does it apply in R. So you can consider, suppose a random sample of size n is classified in 2 categories, all right? In this particular case, you can look at one, for example, one variable, but when you've, there are various categories in it. So we are saying that in this particular case, the chi-square test for the goodness of fit, for you to get the degrees of freedom, it's gonna be k-1. Like as we've been always talking, that k are the number of categories and then the -1 to come up with the degrees of freedom. All right. Now, the formula for us to calculate the expected frequencies for the goodness of fit, as we are going to see, in this particular case, it applies for discrete uniform probability distributions. And we get the expected frequency, which is abbreviated as EI, is equal to n. This is my total sample, n times 1 out of k. Okay, I said n is my sample, and then 1 over k, whereby you can put in the numbers 1, 2 up to k. This is just we assume equal probabilities for every characteristics to happen. So in this particular slide, what I want you to pick out to understand, it's only this particular part, it's the most important, how to get the expected frequency in case of a goodness of fit. Because most of the time we've got the observed counts or the observed frequency. Then how do we calculate the expected, like how we did before in case of cross-tabulation or a contingency table. So here we are looking at goodness of fit. Now, what about the formula? In this particular case, the goodness of fit test formula, like what we had earlier for the case of a chi-square, in this particular case, since we are only dealing with only one observation. So what we do, we get the divergence between the observed and the expected. You square everything, then you divide it by the EI. We've seen how to get the expected, always the observed is given. And then after that, what we are going to do, we'll sum them all up. And this one will tend to a chi-square with k-1 degrees of freedom. And we want to test whether we have to accept the null hypothesis or we have to reject. Okay, so still on this slide, what is important is how are we going to get the t-statistic for the goodness of fit, which we are having here. Okay, initially with the chi-square, we are summing the number of rows and the number of columns. But in this particular case, we are only summing the different the key categories that we have. Okay, let's take an example. So let's assume this particular example. They're saying that a confectionery company is trying out different wrappers for chocolate bar. It's original A and 2 new ones, B and C. Okay, in this particular case, we are looking at the wrapper type. It's only one variable, and with the wrapper type, the original wrapper that was used, that was A, and then they want to see the new ones are B and C. So we want the manager of the supermarket want to see whether getting these other new wrappers can make the sales significant. So we have the new ones B and C. It puts the bars on display in a supermarket and looks to see how many of each wrapper has been sold in the first hour. Okay, with the following results. With the original one, which was A, 8 people bought. Okay, and then with B there were 10, and then C there were 15. So having a total of 33. Okay, and now the question is there a difference between the wrapper types in the customer's choice made? Remember, how are we going to answer that? Looking at, because different customers are showing different preferences of the wrapper types. So we want to check whether there's a difference in preference for the wrapper types, or there is no difference in the wrapper types. So now, if this is our question, the first thing is we need to set our hypothesis. And so the null hypothesis is there is no difference in preference for the wrapper types. And then the other one, that there is a difference in preference for the wrapper types. So let's continue and see. So what we are going to do here, we need to get the expected frequencies, because what we are having, they are the observed frequencies. Later, we are going to take up the condition and check with the tables whether we are rejecting or whether we are failing to reject. Okay, so these are the observed. We are going to push on. Remember, how do we calculate the expected? This is our formula, and that is the sample times 1 over K. And this K counts for my categories. Here I've got the wrapper type, whereby I've got A, B, and C with different observations for each, the observed frequency. So for me to get the EI, remember what we said, we assume that they have got equal chances, equal probabilities. That is the 1 over K. So that in this particular case, I've got my K will be 1, 2, and 3. They are 3 categories for the wrapper type, assuming they've got equal probabilities. So what is going to happen, from my particular question, the total is 33. That is my sample size. So EI will be equal to 33 times 1 over 3, the number of categories, and this will give me 11. So it implies that my expected frequency is equal to 11 throughout the considering A, considering B, and then considering C. So applying the test statistics for the goodness of fit, which I've already showed earlier, this time around, I'm going to sum up to the 3 levels or the 3 categories. In my Chi-square, in my goodness of fit equation, or the test statistics, I feed in my observed. Remember, for the first one is 8, for B it is 10, and then for C it is 15. So when I come here, I just need to start with 1. This is the first one, the first group, the original. This is the second, this is B, and then my C. And so they calculated what I'm having, it is 2.364. Remember how I said the hypothesis, H0, no difference in preference for the wrapper types, and then H1, there is difference in preference for the wrapper type, because by the end of the day, we want to inform the manager whether preference influence the kind of the wrapper type that has been used. So the same story like what we've discussed earlier. This time around, what is going to happen to the degrees of freedom is going to be K minus 1. The category is minus 1. We had 3 of them, so we minus 1, we end up with 2. So we can set the level of significance. You can set it at 5%, you can set it at 10%, you can set it at 1%, depending on your objective or on your degree of confidence that you want to use. So at 5% level of significance, from the table using the new Cambridge statistical tables, it is 5.99, okay? And remember what I mentioned earlier, that in case the critical value, all right, If the critical value or the table value is less than the calculated, we reject H naught. So what is happening here is that now this time around, the calculated value, which is 2364, is less than 5.99. That is for the case of 5%. Okay. Now, in that particular case, since the calculated value is greater than the critical value, what are we going to do? Let me ask in the chat. What I'm having in this particular case, my calculated value is less than the table value at 5% significance level. What conclusion can we come up with there? I'm waiting for answers. Please type in the chat. Are we rejecting or accepting? We fail to reject the null. Okay, that is Robert, Tom. The preference is the same. Okay, accept the null, reject, fail to reject the null. Yes. Okay, that is true. We fail to reject. So again, what about in case we consider 10% significance? With the 10%, the critical value, it is 4.605. So still we fail to reject, meaning that we do not reject H naught, since still the calculated value is less than the tabulated value at 10%. Hence, there is no hence we can conclude that the test is not significant, and therefore there is no evidence of a strict preference for particular wrapper type based on the choices observed in the supermarket during the first hour. So that is the first example that I thought about. But remember, in R, the moment you put the right command, it is going to give you all these results. But like I mentioned earlier, it is great to understand what the computer does, what is the math behind what the computer is giving you, such that you're able to make right decisions. Then let's take the last example on this. It says that many people believe that when a horse race, it has a better chance of winning if its starting line up position is closer to the rail on the inside of the track. The starting position of one is the closest to the inside rail, followed by the second, and so on. The table below lists the number of wins of horses in the different starting points. Do the data support the claim that the probabilities of winning in the different starting points are not all the same? Do the data support the claim that the probabilities of winning in the different starting points are not all the same? So we are given this particular table. We've got the starting points from 1 up to 8, and we've got the number of wins from every position. From 1, there are 29. From 2, we have 19, up to 8, where we have 11. So we want to test that claim, okay? The claim we are given, that do the probabilities of winning in the different starting positions are not all the same. That's what we want to prove. Are they the same or they are not the same? And remember, what we are having here, our variable is the starting points, okay, at different points, and then the wins that happens. So when you look at this particular data, it is discrete in nature. It is a discrete uniform distribution with 8 categories. So still what we said, we assume equal probabilities. So in that particular case, our 1 over k, which is 1 over 8. For us to get n, we need to total the different wins from 29 up to 11. When you do that, you are able to come up with a total of 144. So how do we calculate the expected frequency? Remember what we said, that expected frequency is equal to the sample size, my n, then times 1 over k, the number of categories. And we are assuming that they have got equal probabilities of wins in the different positions. So it will be 144 divided by 8, which is equal to 18. Now, the next step is going to be, we need to fit into our test statistic and see what happens. This is just a table. We've got the starting positions. There are 8 of them. We have the observed frequencies, which are given. we calculate the expected. Remember, in this case, it is the same throughout. So it is going to be 18. We get the deviance between the observed and the expected. So it is 29 minus 18, we get that, and so on up to when we get to 8. Then after that, we can calculate the test statistics for each category. For one, by using OI, the observed frequencies minus the expected squared over the expected frequency. So if you fit this in all this, these are the values that you are going to get. And the moment you sum it up, the total is going to be 16.34. So our test statistic for the goodness of fit, it is 16.34. So what is our, under the null hypothesis, we are trying to check that, okay, let's test as 5% significance level. Then we'll check what about at 1. So, and see whether our claim is supported or not supported. So from our calculation, at the 5% significance level, the critical value, whenever you see the term critical, it implying that this is the value, that it's a tabulated value from the statistical tables. So the critical value is 14.067. That is the tabulated. And the calculated one is 16.34. So 14.067 is less than 16.34, the calculated. So in this particular case, we are going to reject the narrow hypothesis. All right, for at 5%. What about the case? What if we reduce our level of significance to 1% and see? So in case we are turning to 1%, the significance level, when you check in the table statistics, the critical value will be 18.475. Okay, but now in this particular case, the value that we've gotten, it is greater than the calculated value. In other words, the calculated 16.34 is less than 18.45. So in this case, we cannot, the conclusion we are going to come up with, we cannot reject the null hypothesis. So, I mean, depending whether you're looking at it at 5% significance level, the conclusion will be different, the degree of confidence that you want to get. So since at 5%, yes, we are rejecting H naught, we are rejecting H naught and we go in for the alternative. But at 1%, we can we cannot reject the hypothesis. So it depends on the conclusion that you can come up with. So for the case of so we can conclude and say that the test is moderately significant. Why this? Because at 5 it is, we are rejecting the null, yet at 1% we cannot reject the null hypothesis. So there is moderate but not strong evidence to support the claim that the chances of winning in the different starting positions are not all the same. Okay. So I'm going to leave that. It was the part that was remaining on categorical data. How do you test the goodness of fit depending on the data that you have? So what we are going to do now, we are going to move to R and see what about, well, in case you've got a large data set, but you've gotten the theory behind what you want to do, what happens in R. I would also leave this particular exercise. I guess we have these PowerPoints. Then some still like what Harriet did. We can get one person or two to try. You can try on your own, but it also be very good in case you present tomorrow morning. So I'm leaving this as an exercise. So that marks the part of categorical data, and we are going to move on to R. So let me ask in the chat, can I go to R now? Or there is a question. Somebody is saying that Day 9 has not been updated with the material. Yes, Day 9 is not yet there yet, but you have the materials that we are going to use today. They're already there. Okay. I'm going to stop sharing this, and then I share my R script. Please, now let's turn to R. Kindly open your R now, and then we see the data that we are going to use remember, it is called building at categorical data.r script. It is in DES7 folder. That is the script that we're going to use. And the data we are using, it is worksalaries.csv. So in case worksalaries.csv, if you don't have it in DES7, check it in day one, because it is the same data set that we're going to use to see how do we analyze categorical variables in R. Because like we mentioned earlier, it is always important to understand your data, and then after understanding your data very well, it will be easy for you to attach the right statistical test that you want to use. Okay, so what I'm going to do, in case you loaded your libraries already, you can run them, and then you will see in your R console, they will come. Remember, the libraries that you load depend on what exactly that you want to do. R has got over 1 million libraries. So the point is understand the kind of statistics that you want to do and only load the libraries that you want. Okay, so I can set my working directory where my data is. It is in the folder, it's on my computer. So like we've been doing earlier, right now we are importing data. So what you're supposed to do, import data from wherever it is on your computer and bring it in R. So in my particular case, in other words, we are setting the working directory. Okay, so so after here, I'll run that. I've already, remember, how do you set the working directorate? You go to session, set working directorate, then choose working directory. In this particular case, then you have to navigate on your computer and see where, up to when you get the folder where I store the data. But however, I'm so confident that from the different presentations that I've seen, people have now are well versed on how to import data into R, which is a very good plus, because you cannot analyze data unless you've imported it successfully into R. Okay, so I'm going to import my data, which is, I'm giving it, remember, we are using worksalaries.csv data set. In case you want to view, you can click on this icon. You can click on this Excel icon and check the different variables we are having. Please, let's do the same as you do on your computer, but as you're listening, we are having rank, okay, the rank of the professors, which was categorical, professor, associate, and assistant. We've got the discipline, which is A and B, humanities and sciences. We have years since PhD, years service, the sex, and then the salary. So in this particular case, we are having different attributes that affect the salary of somebody belonging to the different track at a professor level. So that is how our data looks like. So what I'm going to do, you can go ahead and check the structure with the structure of the data set. Okay, let me try to zoom out to make my screen, view, then I zoom out. All right, I guess now it is more clearer. Okay, so now I've asked for this, in case you've successfully imported your data into R, I asked for the structure of the data set. So it is always important to first understand whether the way you want your data to look like, it's how R has read it there. So here we are having rank, which is a character, discipline, character, then sex as character. So you need to tell R that no, look at these three variables as categorical variables or as factors. All right, so we use the as.factor command. We've been looking at this. So I'll run that line for the case of rank. I come to that line for the case of discipline. I come to that line for the case of sex. And then I can run again and see whether my structure has changed. So this time around, when you look in the R console, yes, they are telling us, yes, it's a data frame. with 397 observations of 6 variables. Now, the rank is a factor with 3 levels. We have the discipline, it is factor with 2 levels, and then sex is a factor with 2 levels. So now we can continue. I'm well versed that you understand that particular part. I'm not going to go through model building again. This is the part that we looked at yesterday, but I'm going to go direct to analysis of categorical data. All right, since our response variable is salary, so in case you want to check a summary of what salary looks like, it will tell you that the minimum is 57800. Look in the console, the results that we are getting. We've got the median, the mean, the third quartile, and then the maximum. So it is just giving us a 6-point summary with the minimum, the first quartile, the median, the mean, and so on. But remember, in case you want, the point is analysis of categorical data. And we discussed that it is possible to convert continuous or numerical variables to categorical variables, but it is not true the other way around. It is only possible from continuous to categorical, but you cannot start from categorical back to continuous. So because I want to have salary, because I'm dealing with categorical, so implying that my dependent variable has to be categorical in nature, but good enough, I can convert salaries into categories. So depending on the objective that you want, I said, okay, let me categorize my salary into 2 levels. I use low and then also high. So I put it into 2 groups. However, the criteria that I used, I said that I created another variable. Remember, in data manipulation, you can manipulate your data in anything that you want, provided it is leading you to the goal that you want to achieve. So what I do, I create a new variable called SalaryCut. Most of the time, it's good to use objects that will enable you to remember quickly what exactly you're working on. So I used salary categories. So that is why it's SalaryCut. It enables me to remember. And then I go ahead and I use the if else command. If else, like I'm creating 2 options. And the criteria, all the tests that I'm putting, I'm saying that in case the salary is less than the mean, I use the mean as my threshold, 113,706. Call that low, okay? That is the first condition. Otherwise, call it high. This is what this line is all about. In case my salary is less than the mean, which number is 113,706, label that as low. Otherwise, implying that when you see that it's greater than that, label it high. Okay, so I run this line. After running that line, remember I had only 6 variables. I can view and check whether it has been created right. I come and click that, and I can see this time around, I've got another variable that I've created, SalaryCut. And what it does, whenever there is a figure that is less than 113,706, it puts low. And whenever it sees a figure that is higher than 113,706, my mean, it indicates it as high. Okay, let me ask in the chat, is that okay? Okay, proceed, but you move too fast. All right, I'm going to reduce the speed. Great. Maybe the other thing I can still mention, like we talked about data manipulation. You know, this time around I've said you can use 2 categories, but it is also possible that you can create more than 2 categories. Maybe you can say fair, good, and bad. Those are 3. Depending, you can create from 2 and above, whether you want to create it at 3 categories or you want 4 categories, etc. Okay, let's continue. Now, I've seen the view. Now I've created a new variable. So remember how we, in case you want to create frequencies for a categorical variable, we use a command that is table. Okay, for example, I can say table I can say table, and then I tell R that from salaries, then get for me salary cut. Okay. In case I do that, I can run and see. When you look in the console, it is telling you that those in the high category are 168, and then those in the low category are 229. You can go ahead and calculate proportions or percentages, depending. But remember, this time around, we want now to create a cross tabulation or a contingency table. So we are going to consider rank. Already rank, it's categorical. So with the chi-square, we use a categorical independent variable with a categorical dependent variable. And among them, we have the rank. So again, I'm using the table command. This time around, I want to cross tabulate rank and salary cut. Okay. So, and I'm creating everything in the object, my table. Okay. Remember, objects do change. You can put any name. So in case I run this line, okay. So for me to see the output, I come on my second line and I run the object. So when you look at this, with the case of rank, the rank was, we had 3 categories: associate prof, assistant professor, and then professor. So there's what we are seeing here, that an associate, there are 3, remember these are frequencies. So there are 3 associate professors that get a high salary, and with the assistant, it is 0. And then with we have 165 professors that get high salary. And then when you look in here, we've got 61 associate professors that belong to the low category. Then with the assistant professors, there are 67. And then with the professors, there are 101 that belong to the low category salary. So that is our contingency table. Okay, remember, we can, now whatever we are doing, it's what Harriet was showing us this morning. So it was how do you do it manually? But this time around now, we are using a computer to give us everything. Okay, so we can add margins using the add margins command, this one here, but I want to add the margins on my table. So I click here and then I run. When you check now down here, and now the output that I have, I've gotten, and the sum for the first column for high, which is 3 plus 165, and it is 168. The same applies to the row, to the second column, 61 plus 67 plus 101, which is 227. I can also, these are my row totals. Remember, now we can get these are my column totals, so I can get the row totals. So it is 3, for the case of associate professor, it is 3 plus 61, which is 64. And the same applies to the rest. So you can command R to do it automatically. Okay, you can get, in case you want to get frequencies, you can do that. In this particular case, these are frequencies, and these are proportions. You can convert them to percentages and you get out of 100%. And still, we learned earlier how you can round them off to any decimal places that you want. You can still round them to 2 decimal places by using the round command. And we've looked at that before. Okay, I'm going to stop to that. Now let's see let's move on to conducting a chi-square. Okay, now let's conduct a chi-square. So in this particular case, in R uses a command which is chi-square dot test. Okay, and we are running a chi-square. We are considering rank and the salary category. All right, so in this particular case, I'm going to feed everything in this particular command, and then I run that line. So when I run that line, what happened is that in my output in the console, there is the Pearson chi-square test. So I'm looking whether there is an association between rank of a professor and this salary category. Remember, with the category, it is high and low. Okay, before I give my conclusion, let me check in the chat. Looking at the observation that we are having, all right? We are having 2 degrees of freedom. I guess now you know how we come up with the degrees of freedom. We had the 3 columns -1, and then the 2 -1. So it is a 2 times 1, which whereby we are coming up with 2 degrees of freedom. The chi-square has been automatically computed as 1 to 8.62. Remember, we are adding all the chi-square values for each block, if you remember from the presentation. So the total is 1 to 8.62. And this time around, we are going to use a p-value. The p-value we are getting, it is less 2.2 e to the power -16. I want to ask in the chat, basing on the results that you are seeing here, what conclusion can you come up with? Okay, please repeat from categorizing salary. Okay, I'm going to repeat that, but first answer my question. So one is saying that we reject H note, a significant result. Okay, now if you are saying that we reject H note, what conclusion can you come up with? Because for a layman's person who will not understand when you say reject H note, let's come up with a conclusion whether somebody's rank influences the salary. So yes, there is a relationship between rank and salary. Since the P is less than 0.5, there is a significant difference, significant relationship. Rank is statistically significant with salary. A relationship is evident. There is an association between rank and salary. Significant association. Yes, all your answers are right. Thank you so much. And that I also concur with you that it's from the conclusion that we have, yes, we reject H note and conclude that there is a relationship between one's rank and the category cut. Okay, before I proceed, somebody was saying that I repeat from add margins. Can I repeat or I continue? Is it okay, or you've gotten the concept? Can I recap again from salaries cut? Okay. Okay. Somebody's saying, okay, let me recap. Let's go back a little bit and then we'll see how do we get there. I would encourage you that as we are discussing whatever we are doing, trying to see that how can this same knowledge be applied on your data sets or on your work, or as you are anticipating to go to the field and collect data, you also have to have at the back of your mind that yes, I'm going to collect this kind of data, but I think that's the right statistical test that I need to use. Most of the time, your dependent variable influences the kind of analysis that you're going to do. Okay, let me go back. How did we get is the salary cut, how we got the salary category clear? Was that okay? How we came up with this column, salary cut? Is that okay to everyone? Okay. Yes, what was the relevancy? I said why we converted salary into categories. The answer is very simple. The salary that we have in our data set, it is continuous in nature, implying that if we use it as it is, then we cannot use a chi-square because it is continuous, implying that at the back of your mind, you'll have to think of using, for example, a regression analysis, either linear or a multiple linear regression. So, but because we want to do a analysis of categorical data. And already we have our dependent variable salary, which is continuous in nature. But there is an option that you can convert continuous variables to categorical. So it is the reason as to why I converted it into 2 categories, considering low and considering high, such that now I'm able to use the chi-square. Otherwise, if I left it in the state it was when it is continuous, then applying a chi-square will be a wrong method to use. That is the main reason why I created a new category, SalaryCut. And when you view, you see that our variables this time around increased. Okay, so I went ahead. Remember, you can do some simple descriptive, either you can do it in figures or you can do data visualization, depending on what exactly that you want. So with the table, here I was just getting the 2 categories I created. I had low and then high. If you have a quick look at your data set, this is now my dependent variable that I'm going to use for the case of categorical analysis. In case you're using a regression, the one of multiple linear regression, then you consider this one, which is numerical in nature. But with categorical data, we always have 2 or more categories. So in case I come back here, I wanted to see you, for example, you can say you want to see the number of those that belong to the high category and those that are in the low category. So that's why I use the table command. Descriptive statistics, we've been doing that. Okay, then I said, remember with the chi-square, developing contingency tables, the tables that we usually see maybe during when an instructor is giving a lecture, most of the time it is data that is already collected and it appears like that by the end of the day, and then we do the other analysis that you want. So I decide to say I want a cross tabulation or a contingency table for rank and the SalaryCut category. So this is my command, the line I'm going to use. However, I'm storing everything in my table. All right. So when I run this, okay, I want to check the results in my object. What happened is that now this is a contingency table. You can still, you can shift these results into your Word document and just create you create a table and you write the salary category, you put high, low, and then you also put the different levels, associate professor, assistant professor, and then professor, and you feed in your variables. So from what we are seeing, the results, these are the observed, because we are getting them from the data, what the data is telling us. So with these are just observed frequencies. There are 3 associate professors that belong to the high category and 61 associate professors that belong to the low category. We have 0 assistant professor in the high category, and we have 67 assistant professors that are in the low category. I'm trying to read out what we are having, the output that we have. And then when you come to the professor, we have 165 of them who are in the high category and 101 that belong to the low category. All right. And I said, remember with the contingency table, you can add the row margin, you can add the row totals and then the column totals. All right. How do we do that? You use the command add margins. Okay, this is the command that you use, add margins. Which margins are we adding? We are adding for this output here. Okay, and you're telling R 1 and 2, this is the rows and then the columns. So that is the margins that you're commanding R to do for you. So when you come on this line and you run it, check the output now. We are having sums for the rows, the total rows, and then the total columns. So with the first one, with the first row, it is 3 plus 61, which is 64. With the assistant prof, it is 0 plus 67. The sum is that. With prof, it is 165 plus 101, which is 266. Those are the total rows for each category. And then what about the total columns? We can also have the total columns, that is adding downwards. So we are having 3 plus 0 plus 165, and we are ending up with 167 from the illustration we had in the theory. So this time around is the computer that does it for you, but you just need to understand what exactly do you want, and then you command R to do it for you. So from my table, I can still get the percentages. If I take you back just shortly, when you look here, for example, I've got 168 professors that belong to the high category. I can be able to get in case I want to communicate my results, and then I communicate in percentage form. So how do I do that? I use the prop.table. Remember, at the part of the adding of the margins, it also gives you the grand total. So the grand total was 397, which confirms the total number of observations we are having in the data set. Even if when you look here in the environment, it's telling you it has got 379 observations. All right. So from there, in case you run this particular line, you're going to get proportions or fractions. So in this particular case, this one is 0.415. You can change it to percentage, at the same time round it off. Like I mentioned earlier, we've looked at this before. So it's a matter of practicing. And I said that with the R codes, they are reproducible. They're reproducible in the sense that provided you understand what the code does, you can easily shift it from one project to another. But if you don't understand what a particular code does, then it will not help you. Okay, let me pause there and ask in the chat. Are we on the same page there? Okay, great. Somebody's asking, what about for the case of 3 categories? Like we've been mentioning, learning a program, it's a due diligence. So in case as we are learning, for example, here we've created 2 categories, you can ask yourself, how can I go ahead and create 3 categories? Because by the end of the day, this work keeps on changing. Maybe for your case, it might be 3 categories, or you want to put them in 3 categories. And you check, how do I now manipulate the if-else command to 3 categories? But it is doable. Okay. Now, so later I mentioned that you can use the chi-square test in R. Automatically, it will compute for you everything. What you're computing manually, this time around, it's just going to give you all the results at a go. What you have for your case, it is to interpret the results and see how do you interpret your result to a layperson. So when I run the chi-square, this is the conclusion that I'm getting. I'm looking at an association between rank and salary cut. The null hypothesis was there was no association. With the alternative, there is. Okay, so our chi-square is calculated as 128.62 with the DF, which is equal to 2. From what we've been looking at, I guess now you can understand why we are having DF as 2. And then the p-value is 2.2e to the power minus 16. And I'm glad you gave me the conclusions when I asked in the chat that what conclusion can you come up with? Since our p-value is less than 0.05, so we have great confidence that there is an association between the rank and the salary category. Or you can say we are rejecting the null hypothesis. Okay, now you can do the same for the case of sex because it's also categorical, and then for the case of discipline. And you ask yourself, does really sex have an association with somebody's belonging either to a high or a low category? And in this particular case, what we are getting, our chi-square is 2.9166, 1 degrees of freedom. Remember, sex has got 2 categories, even SalaryCut has 2 categories with a degree of freedom, 2 minus 1, 2 minus 1, then you multiply, the product is 1. And here we are having 0.08769. So let me ask in the chat, what conclusion can you come up with when you're looking at sex and the category type? What conclusion can you come up with? There is no significant difference between sex and salary category. So we fail to reject. No association, fail to reject H note, no relationship, reject H note, no significance difference. It is not significant, there is no relationship. Great, that is the right conclusion. All right, so you can try for the case of discipline and move on. Wow, okay, basically, that marks the end of how you can do analysis for categorical data. Okay, you can practice in case you've got your data set, you can practice and see how it works by using the Chi-square test. Okay, before I proceed, I've got questions here that why are we working with the new variable salary category as a character instead of converting it into a factor? Maybe for that particular case, when you can convert it, and because when we run our table, the moment you run the table for the case of SalaryCut, there are 2 levels, and automatically in that particular case it's categorical because R is telling you that high is 168 and low is 122. But in case you want, maybe for you wanted it to look like salaries, I can do that. But I mean, the objective is the same. Salary category, you're signing it as dot factor. Then in bracket, you put salaries. Then SalaryCut. Okay, so when I do that, it's not going to affect my result. And then, sorry, I'm running this line, the one that I've just created as a factor. So then there I can say str and I ask for salaries. It's the same thing. When I run that, it would still show me that SalaryCut, it's a factor. It is not it's not a character. Remember what we said, you convert characters to factor. So I think I've confirmed that. What if you want to use 3 categories? How do you do that? Like I mentioned, whether you want to convert it to 20 categories from continuous to whatever categories that you want, it is very possible. But it is always good that sometimes we need to try on our own to discover something. So I would encourage you to check, how do I manipulate the if-else command in case I need 3 categories. For example, maybe you want to categorize the salaries as low, high, and poor. Or you can say poor, fair, good. Okay, such category. It is very possible. Please try to do that. And maybe the other thing I want to encourage you still, since R is an open source and all these challenges that you're going to face, or we are still facing up to now, the solutions are already there. It's a community. Our community keeps solving all these problems. It's the main reason why we always tell you, always use the latest version. And as you post in Google your question, you'll be amazed to see that already like 100 people or even above 100 have already answered that question for you. Okay, people are still insisting that I should share I should share an example, explain 1, 2 with respect to obtaining the rows and the margins. I've explained that. You're telling R, add for me the total number of rows and the total number of columns. With 1, those are the rows, and then with the 2, those are the columns. What basis for selecting 113706 below salary? With that one, I said it's a criteria. that I chose as an individual. It's not that it is a must, it's supposed to be like that. You can manipulate it to anything. All right, you can manipulate it to anything. But for me, I thought in my thinking, I thought, okay, how can I categorize salary into low and high? And I'm like, okay, let me use the mean parameter as a threshold to help me differentiate those who belong to low salaries and those who belong to higher salaries. Somebody else could say, no, I'm going to use the medium, maybe the mid as my threshold to see that it comes up like that. So it is not a must. It is just something that, you know, when it comes to these commands, you can play around with them basing on what suits your objective. Okay, let me ask in the chat. Are we on the same page? So can I continue? Have we gotten the concept of the chi-square and how you can do it in R? Okay, so I'm giving in addition to the homework that I gave on in the slide, now I'm giving you another homework, this time in R. I want you to use this same data set and use 3 categories for the case of SalaryCut. Okay, you're going to use poor, fair, and then good. Another homework number 2. I'm not writing it down, please listen. Homework number 2, use the same data set, but I want you to now to create a salary category. To create from salary, create for me 3 categories. Use any criteria that you want, and I want 3 categories: poor, fair, and good tomorrow, such that somebody show us on how it works. In case you fail, that's when I'll direct you. But I also want you to try it out and see. So that is homework number 2. Okay, that is homework number 2. We have homework number 1 in the PowerPoint. Homework number 2, using the work salaries data set. All right, I want you to compute for me a chi-square in case your dependent variable SalaryCut has got 3 categories. Use any criteria that you want on how to come up with that. Robert is saying assignment taken. Wonderful, great. So we'll see how you can share with us tomorrow, and then thereafter I'll guide on whether it is right or what can be done. So please note that as well. So this was the practical part for chi-square. The moment you understand the theory, when you come to the practicals, it becomes very easy. So let me ask in the chat, I want to move on to logistic regression. Is it okay? Can I continue? We can go on with logistic regression. Okay. All right. I'm going to stop sharing this. Now check in the day 8 folder. Okay, check in the day 8 folder. It's there. We're going to upload new materials, but these materials are already there. We are going to use the mydata.csv. I'll explain that. Then there is also my data set description. It is there. These are things that you have to check. Then logistic regression.r script is what we are going to use. And then a logistic model, they are the PowerPoints that we will use. The what? Which test can be used in testing the relationship in? How do you pronounce it? Like it. Okay, somebody has just posted a question that what about in case of a Likert scale? Likert, I don't know whether that is the right pronunciation, the Likert scale. Still, most of the time when you come to these kind of questions, if you're doing, maybe you can group it into, for example, maybe strongly agree, neutral, disagree, such questions in that particular form. Since they are also in there, they are categorical in nature, what you can do, you can still go in for a chi-square. Yes, Ronald, a chi-square can do it. If you're doing it, if you want to check the association, still a chi-square can do. You can go in for that. At the same time, or you can, in case you don't want to use a chi-square, but at the same time, if you're looking at those 5 categories and you see at the end of the day, you might face a challenge in interpreting them, you can also try to collapse some of these categories. Remember, you can have, in case there are 5, you can collapse them to either 4 to remove the neutral one and you remain with 4, or you can even collapse them up to 2. It does work. But you have to first, you do it after collecting the data to see that whether, because sometimes you might see that some of the cells are very small, or there you have got no count. Then that's when you can do the collapsing. Yeah, a chi can work. All right. I want to share. Okay, I think. So we are moving on to generalized linear models, and I'm going to start with the logistic model. If time allows, I'll move on to other models, but still my colleagues still have to set in and see how we can see that what we prepared for you is done. So can you see my slides? We're going to go through logistic regression. This is also another common regression model that is used during data analysis. Okay, let's continue. Generalized linear models, of course, there are very many, but now this time around, let's consider the logistic model or logistic models. With logistic regression, what we are going to do briefly, we are going to look at the theory part, and then after that, we are going to move on to R, such that you see how do these things work? How can you explain clearly the results that you've come up with, or how do they come about? So we are going to look at, this is just an overview of what is going to happen. So it is always important to understand the best. We build from the known and then we continue to the unknown. So with understanding the basics, I talked about probability. That is a chance that an event will happen. And we know from the knowledge of probability that we know that probabilities always range from 0 to 1. And then there is a new term that is commonly used when it comes to logistic regression, which you need to put at the back of your mind. It is odds, okay? Odds is the probability that an event will occur divided by the probability that an event will not occur. For example, it is the probability that it will rain over the probability that it will not rain. You're looking at the ratio of two things, something happening to a ratio of something not happening, a ratio of something to fail to succeed over that something that will fail. Okay, so I'm referring to pi as the probability that an event will occur. Let's say that it will rain. And then the probability that it will not rain, it will be 1 minus tau. So in other words, odds is equal to the probability that something will occur over the probability that something will not occur. Or you can use the ratio. With let's take, what if the probability is 0.8, that is 80%. Then the probability of it not occurring, it is gonna be 1 minus 0.8, which is 0.2. So when you get 0.8 out of 0.2, that is what we call odds, or that is odds. Okay, so the odds of an event, like I mentioned, the probability of the event will occur divided by the probability that an event will not occur. So from the previous slide, it's going to be 0.8 out of 0.2, the probability that you're going to pass exam over the probability that you're not going to pass exam. So what are the odds? 0.8 over 0.2, you come up with 4. Another example that you can use, that if there is 80% chance of rain one day, then there is 20% chance that it will not rain as well. So our odds will be 80 to 20. Or otherwise, you can say that it is 4 times more likely that it will rain than for it to stay sunny. Okay. Okay. So with the definition of odds, like I mentioned, this is something that we are going to use even when we are explaining the result. And most of the time, it is important to understand what it is. So it is the probability of success over the probability of failure. So in this case, we are having pi over 1 minus pi, which is equal probability of yes over probability of no. And so we read this as this is the odds of yes. We are taking the odds of success. We are having 2 groups, the yes and then the no. So the odds of yes. So from here, because I know that my odds is equal to this, pi over 1 minus pi, I can make pi the subject and also get to understand what is that pi by just manipulating what I'm having. So the event that has the highest odds is considered the favorite. So if the odds are low, it means that the event is not likely to occur, and the opposite is true. So the odds of price uptake, for example, if I consider that is the probability that the diamond price is high to the probability that the diamond price is low. This was just an example when we're looking at, in case you're considering it, the price of diamond, and we're trying to see the independent variable was the price uptake. So we wanted to see whether people are willing to take in diamond or not. So some of the statistics that is important to look at, for example, like what people have been asking, in case we're having a dependent variable and then we're having an independent variable, most of the time, if your independent variable, like I mentioned, your independent variable drives the statistics that you're going to use. If it is categorical in nature and your independent variable is categorical in nature, you can do logistic regression and then a chi-square test. I'm glad we've looked at the chi-square test, and now we're going to look at logistic regression. I'm saying if your dependent variable is categorical in nature, but still we need to understand to what level, to what levels are we considering? Is it at 2 levels? Is it at 3 levels? And so on. In case your dependent variable is continuous in nature, but your independent variable is categorical, among the many methods that you can use, you can consider an ANOVA or the Carl-Wohl's test. This was discussed by Professor Susan. The other thing, if you're having a categorical variable and your independent variable is continuous, you can go ahead and do a logistic regression. If both your dependent variable and the independent variable are continuous in nature, you can opt in for linear regression or a multiple linear regression. At the same time, you can also use a Pearson correlations. So this is just a summary of the few things that you can use. Okay, so why use logistic regression? Most of the time, logistic regression, there are many research topics for which the dependent variable is limited, okay? And limited in what sense? That the dependent variable is a dummy variable, whereby it is coded either 0 or 1. You can code it 1 or 2, depending, because the coding doesn't matter so much. But what is to understand is that the outcome or the response variable, it is binary in nature. So that's why here we are having binary logistic regression, implying that your outcome of the response, your response variable is supposed to only have 2 possible outcomes. For example, either you vote or you don't vote. Okay, in case that is a dummy variable, you can code it as 0 or 1. Okay, another dummy variable, you can say admitted or not admitted, success or failure, 2 outcomes from 1 response variable. All right. So like on this example, what we are having, still we are looking at categorical variables that are binary in nature, whereby you can apply logistic regression. So here there are two things, my Y response, the Y is the binary response, okay? Or call it the dependent variable, or call it, because it's a one, we are looking at factors that are going to influence the Y. So in the first one, the response is whether somebody is a non-smoker or is a smoker. And then, or another example we can take, in case somebody is treated, success of treatment, of medical treatment, the response, if somebody is under treatment, either this person survives or this person dies. All these possibilities, the two possibilities that we are seeing, they have got a binary response. So we can go in for a logistic regression. Okay, so with the proportions of success, in a non-linear regression, the model can be, you can be able to predict the mean Y for any combination of predictors. But in this particular case, when we come to logistic regression, we are looking at the mean in this particular case is a dummy variable, and we're looking at the proportion of success. That is our pi, okay? The proportion of success, the proportion of something that is going to happen, the event is going to happen. So most of the time, the goal of logistic regression is to predict the true proportion of success, that is our pi, to considering any predictor variable. You can use either, they could be continuous or they could be categorical. Okay. As far as today's material is concerned, don't check for materials for day 9. You already have the materials. Please check in the Google link. Like I mentioned that at the start, we are using materials in day 8. In the day 8 folder, you're supposed to get this PowerPoint that I'm explaining. Then you're supposed to get the logistic regression.r, and then the mydata.csv, and the description of the data set. So today we've not posted any material yet because you already have the material that we are going to use. We'll upload new material for tomorrow, but today we have what we are supposed to use. Okay, so moving on, we are still talking about the binary logistic regression model. Remember what is important here, your outcome variable, it's a binary response. And then the X, these are the explanatory variables or the quantitative predictors. So our main aim is to check the proportions of the success, how the predictors affect the binary outcome. So, like, we'll move on this the equation on how you can write a logistic regression. So it is of the form that log of pi, this is the probability of success, over 1 minus pi. Remember, when you're looking at the case of multiple linear regression, we had Y here, that Y was equal to beta naught plus beta 1, X1 plus, and so on. Okay, we are looking at the relation, how the different independent variables influence the Y. Okay, which Y was continuous in nature using multiple linear regression. But when it comes to logistic regression, this time around, instead of Y, we are looking at it in terms of the proportion of success. And in this case, it is the log pi, the probability that of success over the probability of failure. This is an odd. So, which is equal to beta naught plus beta 1x. This is a simple logistic regression. I'm calling it simple because it's considering only one variable, only one independent variable. For example, you can say age. Okay, and we are reading this as the log odds because these are odds. Yes or no, the log odds is equal, it's a function of different dependent variables. But still, you can write this in probability form by taking the natural logs on both sides. And then when you take the natural logs on both sides, you make pi the subject, you'll come up with this kind of representation, that your probability of success will be equal to e to the power b naught plus beta 1x then over that. All these things can be done, can be proved mathematically, but now we are just getting because we are looking at how they can be applied, let's understand how they work. Okay, so the first one I considered in case of a single predictor, that is one dependent variable, one independent variable, or you can call it an explanatory variable. So the logit form, like I've showed, it is this one, and then in probability form, it is this kind here. Okay. So what about the case if you're using, in case you're using multiple independent variables, multiple in the sense that you have 1 up to k independent variables. So still, remember, now what is going to change is your right-hand side. Instead of only having one independent variable, we are going to have many other independent variables, but the story remains the same. And we can as well still take the natural logs on both sides and make pi the subject. We come up with that. Remember our x's, that the beta ones are the regression coefficients that we need to calculate. And what is making it a logistic, remember the link here we are having, it is changing. It is an odd, a yes or no. So the log odds for the, here we've got a success over failure and is equal to that. Okay, most of the time, the logit function is S-like when you Google and look in different textbooks. That's how it's in the signal form. Okay, let me explain this, then we continue. So here, still I'm looking at odds. I've already explained this, the logit form on how it looks like in case of a simple linear regression. So most of the time, the logit mode assumes a linear relationship between the predictors and the log odds. The predictors are the ones that on my right-hand side, and then the log odds. The log odds emanates from here. Pi over 1 minus pi, these are my odds, and then the log. So that's why it is this statement that what it does, it assumes a linear relationship between, we've got a linear relationship on the right-hand side, okay, between the predictors and then the log odds, which is this particular side here. And with this one, we've seen it already, that I know that my odds is equal to pi, the proportion of success over the proportion of failure. And we can still manipulate this and come to that. So we also what we call the odds ratio. How do we get the odds ratio? This one is good when you're comparing two groups, okay? A common way to compare two groups is to look at the ratio of their odds, all right? And in this particular, remember what we talked about, the odds. You can have, for example, for the case of, let's consider sex. And in sex, you've got, maybe you have female, you have males, okay? At the same time, maybe you're considering e-learning, e-commerce uptake. Let's consider that. Some do they take it up, others do not take it up. So between these two groups, we have the females that take up e-commerce and we have the females that do not take up e-commerce. That is one group. We have also, and from the females, we can get an odds, we can get their odds. And then we have another group for males that can take up e-learning, who agree to take up e-learning, and then you have another group that does not agree to taking up e-learning. That is also another group, and we can get their odds. So for the odds ratio, you get the odds of one group, you divide by the odds of the other group. In this particular case, the odds of female divide by the odds of the males. That's why we are calling it odds ratio. comparing two groups and you're looking at the ratio of the odds of the different groups. And so most of the time when you're doing the analysis, especially when you're reporting your results in maybe you're writing a publication, we report odds ratios, as we are going to see. So an odds ratio greater than 1 indicates that the condition or the event is more likely to occur in the first group. And in case it is less, that is if it's greater than 1. If it is less than 1, then the condition is the event is less likely to occur in the first group. Where it is greater, that it's more likely to occur in the first group, the one that you're comparing with. And then if it is less than 1, then the chances for it to occur in that group, it is minimal. Okay, let me ask in the chat, are we still on the same page? Okay, great. Let's continue. In case you have got questions, please post them in the Q&A. My colleagues are here. They will be able to answer them very well. If you feel there is something that is not clear as I'm pushing on, post the question in the Q&A. You'll get a reply. So also there is something important that we have to note at the back of our mind. I've talked about probability, I've talked about odds, I've talked about the log odds. All these concepts, you need to be familiar with them. In case I've got the probability of, but my probability of success is mu. I'm just putting mu, but you can change it to anything. So my odds will be the probability for occurring over not occurring. So it will be mu out of 1 minus mu, like the examples that we had. And we can take the log odds. For the log odds, you just take the log and then the odds that you're having here. Okay, in case you've got, you look at it in terms of probability that my event of success, y is equal to 1. So the odds will be the probability of success out of the probability of failure, y over 1, yes over no. Then you can also consider in terms of log odds by considering this. Okay, most of the time you when you are considering probabilities lie between 0 and 1. But as you're moving on to log odds, you're able to logistic regression supports you to move from the bound to unbound. For example, in case you have your mu equal to 1, okay? When you get the odds of 1 out of 1 minus 0, this is going to be infinity. And so when you take the log of infinity, those are the odds will be infinity. In case you're considering maybe the middle, that your mu is equal to 0.5, taking the log odds, it will be 0.5 over 0.5, which is 1. The log of 1, my odds here, it is 0. In case it is 0, you're going to come up with 0. The log of 0 is infinity. So in this particular case, what you're trying to do, you're transforming from bounded to unbounded. For the case of the probabilities, they are limited between 0 and 1. When you move to the log odds, you are able to shift your values from minus infinity to infinity. And that is the instance of why we are having log odds. So let me give a simple example of a simple logistic regression. Remember from what I showed earlier, maybe I go back a little bit. When you look at this one, it is beta naught plus beta 1 x. This is a simple example. This is an example of a simple logistic regression. I'm considering only one variable. X can pick up any variable. It can be continuous or it can be categorical. And remember the link function, in this case, it is log, it's the log odds, the probability of success, that is the yes over the no. So let's go back and see. In this particular example, this is a simple logistic regression. I've got my beta naught, that is my intercept. I have beta 1, this is my slope, and my x, I'm considering gender. Okay, and this is my log mu over 1 minus mu, my log odds, depending on what I'm studying. So, but looking at this, gender can take up two levels. Either somebody is a female or somebody is a male. Let's assume that If it's a male, you come up, gender will be equal. If it's a male, it is 0. If it's a female, then it is equal to 1. So in case I'm considering gender equal to 0 for the case of male, it implies that I'm going to come to my equation here, and then I write 0. And then in case if I put 0 here, it implies that I'm only going to remain with beta naught. Okay, in case I consider my gender as 1, when I put 1 here, it implies that I'm going to have my log odds to be equal to beta naught plus beta 1. Let me ask in the chat, is that equation okay? A simple, the simple logistic regression, is it okay? All right. In case something is not clear, post the question and then more illustrations will be given. Okay, Bernard is saying for now. All right. So let's move on. Now, when you move on for the case of a simple logistic regression, like I said, the beta naught and beta 1, these are estimated regression coefficients. Let's assume an example of our response variable as uptake of e-commerce, and the response is either yes or no. Okay, and the response variable, that is our dependent variable. And our explanatory variable is gender, like what I've been showing here. And we are having male equal to 0 and female equal to 1. So in case we go back to the previous slide here, when we put in our 0, you find that we get log odds equal to beta naught. When we put in 1 for female, our log odds will be equal to beta naught plus beta 1. So for the case of gender equal to 0, so we are going to remain with it. We are going to come up with our log odds to be equal to 1. So how do we read that? We are going to read it as the log odds of uptake of e-commerce among female students. Remember, we are looking at e-commerce uptake. That is the odds here, e-commerce uptake. So the log odds of e-commerce uptake among male students, because our gender here is 0. Okay, in case we put 1 here, we are going to remain with beta naught plus beta 1. These coefficients will be calculated in R automatically, but the main message would be so we'll read it as, it will mean the log odds of uptake of e-commerce among female students. So the coefficient would be beta naught plus beta 1. If you have it at the back of your mind, even you can go in R when you're doing R and see when you sum up, do you really come up with that? So this is the explanation I'm having here. I'm considering only a simple example whereby, of course, with binary logistic regression, it's a yes or no. So we are looking at uptake of e-commerce. You can look at anything, or maybe the chances of somebody being admitted in the university and so on, but it's a yes or no. Okay, when I looked at gender as my explanatory variables, in case I put in 0, what should come at the back of your mind that will refer to, those will be male. So it will be the log odds of uptake of e-commerce among male students. If I consider for 1 the gender, those will be log odds of uptake of e-commerce among female students. This is what this equation implies. Okay, it is always good also to note that from log odds, we can get odds ratio. I've mentioned that the OR. How do we get that? We do take an exponentiation of the value of the log odds. And like I mentioned, most of the time, if you're going to report your results in your publication, we'll use odds ratios. We have another example here, and it's talking about the relationship between treatment and pain relief. Okay, here I'm having a response variable that is pain relief or pain-free, and it also has 2 categories, yes or no. Some people, and then the explanatory variable, I'm using TMS, all perceived as treatment. So there are also two groups. The treatment, it's for treating migraine. Okay, and also there are 2 groups. All right, I've got the response and then the explanatory. I want to check whether what I want to achieve, if the treatment given supports pain relief or not among these two groups, the group that take the TM treatment and the one of placebo. So this is the table that I have. Okay, I've got TMS, I've got the placebo. So this is my dependent variable. I have got a yes or no. Okay, here there are 39, those that take TMS. Those who said pain relief, they are 39. Those who said no, they are 61. So this is one group. I've got another group that is for placebo. The one that says yes is 22, and the one that says no is 78. Remember what we do? We need to calculate the odds ratio for TMS. How do we get the odds ratio? It is yes over no. So in this case, it's going to be 39 divided by 61. So the odds are 0.639. And then for the placebo, the odds is going to be the yes over no, 22 over 78. And I'll come up with 0.282. So since I've got if this is my first group and this is my second group, so for me to get the odds ratio, then it's going to be the odds of TMS over the odds of the placebo. And it's what I'm having in the second slide. So the odds ratio will be equal to the odds of using the TMS for pain relief over the odds of using placebo for pain relief. So in this particular case, when I refer back to my previous slide, I'm going to get this. I divide it by that. So I'll end up with 2.27. So since now I've gotten the odds ratio, when you look at the results that I'm getting this time around, it is greater than 1, 2.27. So there are different ways on how people can interpret these the findings. But one of the easiest way, you can say that the odds of using the TMS for pain relief are 2.27. You quote the odds ratio times the odds of using placebo for the pain relief. I get this interpretation directly from my formula here. The odds of using the TMS for pain treatment. Remember, TMS is one group, and then I have another group that takes placebo for the pain relief. So you can have that. That is a direct interpretation. Or somebody else can say that TMS treatment is 2.27 times more likely to relieve pain than the placebo. We are comparing two groups. So that is another example, but we are still going to move to R and see how it works. In case the same data is put in R, okay, I'm considering the same data being put in R. What we are having, we are in R, we are going to use the GLM command. Here there's CB, yes and no. This is my binary outcome, my Y or the response, which is a yes or no, but we are going to look at another one, how you can write it. And then as a function of the two groups. In this part, the two groups we are having is the one that is taking the TM treatment and then the placebo treatment. So this is then family, we are going to say it is equal to a binomial because we have a binary output. Like we did in regression, you have to indicate your data is equal to TMS. But in this particular case, instead of LM, we use GLM. And you can also create an object. From your object of LMOD, you have the summary, okay? You can get the summary of your output. And then you can now go ahead and you have the estimates, the standard error, the Z value, and the P values. And now you can go ahead and explain what these results are. We are going to go into more details when we get to R, but I just wanted to show you a feel. Like I mentioned, from the estimates that we have calculated, you can be able to get the odds ratio. How do you do it? You get the exponent, the exponent value of the estimate. Like in this particular case, when you come to the group of TMS, remember these were 2. So it implies that a placebo is used with, it is treated as a dummy variable, and the placebo is the reference category. So what am I communicating here? That you can get the odds ratio by taking the exponential of the estimate. In this particular case, it is E 0.8184, which is 2.27, and this is our odds ratio, which we got earlier in the previous slides, which we got in here when you're calculating it manually, which is 2.27. So still R is the same value that it's giving you, whereby we mentioned that we are looking at the odds of using the TMS for pain relief to the odds of using placebo for pain relief. Okay. Yes, I think now we can move on to R and R Studio. Let me ask in the chat. Any question? Yes, Robert, you're right. The TMS is 2 times more effective. Somebody's asking about the ROC curve. I think post that for Professor Susan to answer. Needs more details. Prof, there's a question. Why do you prefer logistic regression over, and both is applicable in the, we only apply, yeah. Okay. Okay. So when it comes to logistic regression, we are considering binary outcome, 2 binary. Yet with the probit, if you're dealing with proportions. So what is the difference between response variable and explanatory variable? The response variable is your dependent variable. Then explanatory is your independent variable. These words are just used interchangeably, but they all mean the same thing. We are going to do that more in R. Okay, so can we go to R? Can we move on to R and get more details? Please post the question in the Q&A. Post the questions in the Q&A, and then in case there is, then they will be answered. So let me stop sharing that. Sorry. Okay. Okay, now let's move on to R. In this part, we are going to use, if you check in the, we are using day 8. In day 8 folder, please download the logistic regression, logistic_regression.R script is what we are going to use. We are going to use my data. Okay. Okay, we are going to use my data, and then I want us to first share how the data looks like. It's what I'm trying to. Okay, all right. So let me first stop sharing this, and then I talk briefly about the data that we are going to use, and then I'll share again. So my data. Okay, yes, I've seen it. Okay, so this is let's go through the description, and then I'll show you the kind of data that we are going to use, and then we continue. So this is the description. Most of the time, especially in case there are some people or individuals who are using secondary data, it is always important to first understand the meaning of the respective variables that we are collected, because unless you've got the background information on what this data is all about, it won't make any sense at all for you in the data that in the analysis that you're going to do, and it will become very complicated. So it is always important to have background information in case it is not primary data. Okay, with the primary data, it's okay. But with secondary, it is always important to understand how that data was collected. And most of the time that information is available attached to it. How was it collected, the different sampling procedures, and then what reason was that data collected, and then what possible objectives can you formulate in the data that you want to use. So here they are saying that a researcher is interested in how variables such as GRE, that is the graduate record exam, okay, it's what we are having, and GPA, that is the grade point average. GRE, graduate record exam score, then GPA, that is the grade point average, and prestige of the undergraduate institution. Prestige of the undergraduate institution affect admission into graduate school. Okay, so we are having, and then the response variable, the response, which is the same as the dependent variable or the outcome variable, is admit stroke do not admit, is a binary outcome. Since it's a binary outcome, so we can go ahead and use a logistic regression. So with the, I'm calling the data, my data. The variables, GRE, the grade record examination score, it is continuous in nature. The GPA, the grade point average, it is continuous in nature. And we are told that rank, that is the prestige of undergraduate institution, it is categorical. And they're saying that rank takes on values 1 through 4. So we have got we've got 4 levels or 4 categories. Institution with a rank of 1 having the highest prestige, while those with a rank of 4 have the lowest. So we have from highest, maybe you have from the highest prestige, then to the lowest prestige. There are only 4 institutions. And then admit is our response variable, which is either you are admitted or not admitted. So in this data set, we are having 4 variables. The admit, which is our response variable, either somebody is admitted or not admitted. The GR, which is a continuous variable. The GPA, which is also continuous, and prestige, which is categorical. And they are saying that they run through from 1 to 4, with 1 with the highest prestige up to the lowest prestige. So now the goal is to clarify students' applications, whether they are admitted or not admitted. In other words, or they are rejected. So this is the background of the data set that we are going to use. Okay, I'm going to stop sharing this. Now I share the data set itself. So what I'm showing is what I expect you to download from day 8 folder. Okay, this is how the nature of the data looks like. We are having admit with 0 and 1. 0 not admitted, 1 admitted. We have the GRE, which is continuous. We have the GPA, which is continuous. We have rank, which is categorical, from 1 to 4, whereby 1, that is the top prestigious, up to the 4th one, which is the lowest. So now we are going to go into R, given this kind of data that we have, and see how can we come up with now, how can we discuss the factors that affect somebody's admission. Which factors are GRE, GPA, and then the rank. I'm only considering a simple data set, but of course you could be having a larger data set. The point is taking the message home. Okay, now back to R. Let me ask in the chat, are we all on the same page? Have you been able to download the material? Could you please post the registration? Please, everything has been posted. Check in the chat and get the. Today we are looking at registration for day 9. Kindly register in that. And then YouTube has been posted, and then the Google link where the material are. So check in day 8 and get logistic regression.r script, pick the mydata.csv. It's what we are going to do. It's what we are going to use. Will you please take us through the R markdown? Okay, we'll see if time allows. So now, what we are going to use the logistic regression R script. Like I said, we keep on building. I can clear my console by you click Control L, you clear your console. I also want to clear my environment such that I see closely what exactly I'm doing. So when I run that, my environment becomes empty. Okay, so now what I'm going to do, I'm good to go. I'm going to run my packages, the packages that I need. We already have these particular packages, and make sure that they are installed. So I can highlight and run all of them. I'm loading all of them. In case you have some packages that are not yet loaded, please go ahead and load them. I set my working data. We are importing, the point is that we are importing data in R, okay? That is reading data into R, okay? This is my, I'm setting my working directorate, all right? So if it is right, I'm reading my data into R, which is, I use the read.csv, my data. So when I read in, when I check in my environment, it is showing me that the graduate data with 400 observations of 4 variables has been imported, has been successfully imported in R. So let me ask in the chat, have you been able to import your data successfully in R? Okay. Please import data in R. We are importing the mydata.csv. In case there are packages that required, please install them. Right now, I guess we are able to install all the packages that we want. You install and load. Okay. All right. So I can be able, remember the command head, we tend to, you use head in case you want to see the first rows of your, the first 6 rows of your data set. So it is showing me that admit, I have the GRE, the GTP, and then the rank. So this is what I'm having. I have 01, the GR, and so on. I can get the structure by using STR. It is always important to do these basics and see whether what you want is what R is, or R is talking the same language like Q. When you look at the data frame, admit it there, for it, it is seeing it as an integer because it is 0101, okay? And then the GRE, it's an integer. The GPA, it's numeric. And then rank, it is also seeing it as an integer because they are numbers. So what we are going to do, we want to convert admit to tell R that it's categorical, and then rank that it is categorical. So when I do that, I use the as factor command, this one here. I want to convert admit, and then the one of rank. I'm telling it there are factors. Then I can run my STR again. So in this, now things have changed. Admit, it's a factor with 2 levels, which that is 0 and 1. So it has put it right. And then the rank with 4 levels, that is 1, 2, 3, and 4. Then the rest, they can remain the way they are. So what we can do, we can run a 2-way contingency table of the outcome and then the predictor variable. Okay, so like we did for the case of a chi-square, even when you're going to do a logistic regression, because that is for the case of at multivariate level. In case you have a variable that is categorical in nature, you can first do it bivariate by looking at the chi-square, and then the factors that you find that are significant are the ones that you can push and take to logistic regression. So depending on how you want to do analysis, most of the time we start with the univariate, and you can do some graphics, that data visualization. After the univariate, in that particular case, that is the descriptive, considering only one variable. Then you can move on to bivariate. With bivariate, you're considering association between 2. And most of the time at this particular stage, when doing bivariate analysis, whatever is significant is what you push onto the second level. So in this case, in case you're considering a table, okay, and then you are looking at you're considering admit and then the rank. So you can go ahead and do a chi-square like what we said, because it is possible. If it is significant, you push it to logistic regression, depending on what exactly you want to achieve. So here I'm having table. I'm using the table command. I can run that one. So what is showing me, remember with admit, there are 2 possibilities, 0 or, you're either admitted or not admitted. And then with the ranks, I've got being admitted in the prestigious institution. There are 4 institutions, 1, 2, up 3, with 1 being the highest, and then in that order up to 4, which is the lowest. So when you look at our outcome here in the console, what we are seeing that those who are not admitted in category 1, that is in the highest prestigious institution, there were 28. And those that were admitted, we had 33. Then those students that were not admitted in the second institution 2, there were 97. Those that were admitted were 54. When you come to 3, 93 were not admitted, 28 were admitted. And then to the 4th one, we have 55 that were not admitted, and 20 and 12 were admitted in the 4th institution. In case you don't want to do it that way, you can also use the xtabs command. Even this one here will give you the same output. So depending on what you want to use. So I'll skip that. All right. This again, I ran my STR. I think we've already seen that. We already have that. Now I go ahead and start to write my equation, a simple logistic equation. If you remember very well what we said when it comes to a simple logistic regression, maybe let me share a free Word document, and we go a little detail such that we understand the things very well. Okay. Okay, remember what I mentioned earlier. You can you can insert okay. So we are having here, it's going to be admitted. Then down here, we'll have not admitted. So this will be equal. So that will be equal to, I'm going to have my beta note. I'm using, so I can have slash beta note. So I can have beta note, and then I can have beta 1. Then here, maybe like in this case, I can consider the GRE, and then yeah, as my, so here I can say log. This is log of everything. So looking at what I have here, this is L, the log odds of a candidate being admitted. Okay, so the odds are admitted over not admitted. Let me make this one bigger. Yes, let me put it at 20. So I've got the log odds. My odds is admitted or not admitted. And remember, we said that for a binary logistic regression, it looks at the relationship. It looks at a linear relationship of the predictors or the independent variable and the log odds. So here I've got the log odds, then I've got my beta naught, the regression coefficient, and then my beta 1 is the slope. And then I've got time was the GRE. This GRE is one of the variables that we are considering. And then you can write the same equation in case you're considering, in case I'm using the same, here I can put rank. Okay, in case I'm considering my categorical variable. This was for the case of continuous, this was for the case of categorical. Or you can write, this is simple because there is only one independent variable. However, you can consider others, and then you write plus. For example, you can say insert. I want to pick. For example, I can say beta rank. This becomes my beta 2, then rank. Then I add. I can have beta 3. Then the other one was GPA. Okay, so this is what we are having. For a case of a simple, it is only one variable, like GRE or rank, it's only one variable. But in case it's now with more predictors, I can have that, I can have rank, then I can have the GPA. So this is what we are having. Remember, this is our link function, the log admit over not admitted. So either with admitted it's 1, not admitted is 0. So we read this side as the log odds, which is equal to the relationship of the other independent variables. So this is how things look like. So now let's go to R and see, in case I'm considering a simple logistic regression. This one is a simple logistic regression. The same applies to this, but this one is multiple. Multiple in the sense that it has got more variables. Okay, I'm going to stop sharing this. Now I share my R again. So now let's start. We are looking at a simple logistic regression. So what are we using? This time around, instead of using LM, which stands for linear model, we are using GLM. The GLM, now it is a general linear model. What we are having, we are going to start, we know that our response variable or the dependent variable is admit, which is binary, okay? And we want to see how it is being influenced by somebody's GPA. I'm only considering the first one, that is the simple logistic regression model. We also indicate data. Okay, my data is graduate. This time around, the other argument that we include is family. And we're telling R that we are pulling everything from the binary family. And we are considering first with a continuous variable, which is GPA. Somebody else, in case you want to learn more info, you can say question mark, then GLM, and you ask R. When you run that, when you come to the help window here, fitting general linear models, you can see the argument. They're telling you that GLM is used to fit generalized linear models, specifically by giving a symbolic description of a linear predictor and the description of error distribution. How is it being used? This is what we are having. We are having, you have to state the formula. The formula in our case, it is admit then the function of GPA. You have to state the family, because I mean, there we have got very many generalized linear models. So you have to state it. You also have to state your data and so on. Of course, there are very many other things that you can also state the method in case you're interested in that and so on. Then we have, when you move down, they are explaining everything that you need. It's also important to use the help function in case there are some things that are not clear. So they tell you, you indicate the method, you put the model, and you proceed downwards, and so on. And what is interesting that even R goes ahead to give you some examples. So when you scroll down further, you see that there are some examples that are being given to you that can help you to understand what you're doing. Okay, so now back to what we are doing. Let me zoom in such that, yes, it becomes more bigger. All right, so here we are. Now, in case I run GLM, I've indicated family binomial. Remember, our outcome is binary, yes or no. And then we indicate the data that we want to use. So in case I run this particular line, okay, now I come and ask for the summary. I stored everything. I stored this equation under the object called logit. So if I run that, I can come and say, I want to get what logit is. When I run this, what it will do, it will only give me the coefficients. If I run only logit, it calls for me the formula that I've used and the coefficients. I'm having the intercept. At the same time, I'm getting the GPA, the degrees of freedom, the residues, the narrow divergence, deviancy, and then the residue deviancy plus the AIC. But like I said in case you need more details, you can just type summary logit and then you run this. So what happens in this particular case, it gives you now more information. Initially, it was only giving you the estimate, but when you run the summary, it goes further to give you the standard error, it gives you the Z value, it gives you the divergence residues, and then you come here and have the p-value. So in this particular case, what we are having, we have the intercept, the estimate, which is minus 4.3576, the GPA estimate, which is 1.0511, and then when you look at the p-values, like they have been interpreting before, when you see that your p-value is less than 0.05, what comes at the back of your mind that this variable is significant? Okay, so in case you want to write out your equation from here, so it's going to be minus 4 points. So you're going to write log odds, which is kindly look at what I've highlighted in the RStudio. So you write log odds, which is equal to minus 4.3576. That is my intercept beta naught. Then I add 1.0511 times my independent variable, which is the GPA. So this is how my simple linear equation, my simple logistic regression will look like. That in this case, the log odds will be equal to minus 4.3576 plus 1.0511 times the times the dependent variable, which is the GPA. Let me ask in the chat, can there be somebody who can help me to interpret? How am I going to interpret how can I interpret the result, the estimate results that I have? Post in the chat. Can you post in the chat? I'm waiting for you. How can you interpret the estimate? So somebody saying that we can take a natural log. Okay, we are going to go to that. Somebody else. We can take a natural logs. Remember what we said, in case you're to take a natural log, then you're going to come up with the odds ratio, because most of the time odds ratio are quicker to interpret than just reading out the estimates. The log odds of being admitted increased by 1.051 odds by GPA. Okay, admitted is significant predictor of GPA. The higher the GPA, the more likelihood, probability of admission increases by that. Okay, we take the exponent of the odds. Okay, let's continue. Thanks so much for those that have contributed. So what we are going to do, like I mentioned earlier, that most of the time, it is always good in case you're interpreting the result. Because when you look at this particular equation here, maybe if we are to use what how we've been explaining the regression, the equations. So somebody can say that for a unit increase in GPA, okay, it will increase the log odds of somebody being admitted by 1.0511, isn't it? Because that is what that is one of the comments that somebody has shared, which is very true. However, in case you want now to zero down on how you can put your results, in case you want to publish them and they become more meaningful to the community, what we say that we need to get the odds ratio. How do we do that? We can take the exponent of the estimate. In this particular case, our estimate for the GPA is 1.0511. So we can use the EXP. This is the exponent command, and then you dial in the number, which is 1 or 1.0511. When you run that particular line, you come up with 2.860796, which you can round off maybe to 2.86 or 2.9. However, also in case you want to do it, another option that you can use, you can just come and say, we know we've got this particular command, coefficient of your object. Maybe I can come here and say coefficient of my object, which is logit. Okay, with that one, you're telling R that only draw for me the coefficient from this model. When I run that, this is what it is giving me, that the intercept, the coefficient for the beta naught is minus for that. And then my GPA is this. So now I can now just come and say the exponent, that is the exponential of my coefficients, and I run that. So when I run, I'm still coming up with the same answer. In the first one, I only consider that GPA, but now here it is giving me the odds ratio by taking the exponent of beta naught and my GPA, which is the same answer, 2.86. So remember how you read categorical values in a logistic regression. It is different on how you read continuous variables. So in this particular case, if you remember clearly our equation, which is the log odds equal to minus 4.3576 plus that. Now we are given that the odds ratio is 2.86, okay? And GPA is continuous. So how do you read this? We say that for a unit increase in the GPA, the odds, remember we've taken we've exponentiated this particular, the estimate. So the odds of being admitted, increase by this particular factor. The factor is 2.86, or you can say 2.7. For a unit increase in your GPA, the GPA of a particular candidate. So the chances of this person to be admitted, so they will increase by factor 2.86. That is how we read out a continuous variable. Remember, our GPA is continuous, so it is somehow related to how we are reading our results in multiple regression. However, this time around, we are putting odds because we have a chance of somebody either being admitted or not admitted. But our pie is that we are looking at what are the chances of somebody being admitted. So we conclude by saying for a unit increase in the GPA, the chances of somebody being admitted, they increase by this factor 2.86. Let me ask in the chat. Okay, let me ask in the chat, is that interpretation fine? Maybe somebody else can have another interpretation, but the point is that, I mean, you're coming up with the meaning the audience can understand, and that is the right way of how you can interpret the results. Anyone with a different, the different composition and how we can interpret the results, maybe you might have learned it in a different way. Okay, how can you, yes, Reinhard, you can send in your contribution in case you're using marginal effects. How do you interpret that? Okay, logit not found. Logit is an object I'm using. Maybe you change it to something else. But in case you're running, if you've loaded all the libraries and you're running line per line, then you should not have that error. If I'm to take you back briefly, I used logit as my object, but you can label it anything. So it's what I'm carrying through. I call that model logit. That is after using the the GPA. Okay. Also, I went further and considered, I went further and still when you come, I created another object, logit 1. So in this one, I used the GRE. Remember also GRE is a continuous variable. So in this particular case, what I did the same thing. What I changed was only my GRE. There is nothing else. So in case I run that particular line and I ask for, this time I called it logit 1. Please don't confuse it with the first one. I got the summary of that. Let's see the output. What happens this time around, even the GRE is significant, okay? So you can go further and compute, we've got the estimate, we've got the PRE, so you can come up with, then you can write out your simple logistic equation, all right? You have the intercept and then you're having your slope. In case you just want only the odds ratio, you want to interpret the odds ratio, you can get this command and you put logit 1. The moment you run that, for it is 1.0035. So you can still come up with the same conclusion. You can interpret it and say that for one unit increase in GRE, the odds of being admitted increased by this particular factor, 1.004, or you can say 1.0036, that way. All right. Now, that one was looking at how you can interpret continuous variables. Let me ask in the chat, are we on the same page? If the factors are kept constant for every unit. Yes, Amos, you're right. I've seen your response. You're very correct. Thank you. That's a good one. Okay. GPA increased log odds by 1.05. Okay, great. We break. At what time? Right now. Okay. So Stephen is asking, how about the odds at particular level of independent variables? It's what we are going to look at. When do we use more likely, less likely, or equal likely? We use that particular interpretation in case you're comparing two groups, if you're moving to categorical variables. So we are going to do the interpretation when we are considering a categorical independent variable. Okay, Fred is talking about a break. I think keeping factors constant is the scenario of multiple regression. We finish this script and we break. Okay, let me ask, can we take a break now? We take a break or I continue? Okay. Up to what time? 15 minutes will be enough. That is 12 what? Break of, yes, we are going to have a break of 15 minutes. Please don't go away. And at 1, isn't that a lot of time? Let's start at 12:50. Samuel, thank you. 12:50, we are continuing. Okay, let's take a break. At 12:50, we continue. Yeah. We are taking a break of 15 minutes. We are returning at 12:50. Oh. Poison, you know. Mhm. It is the same, only that like the way you come in the morning and do some little adjustments. They have gone for a break. I'll send the moment they come back, such that they pick it. Baliwa, bana. Ngabya jasomesa yangambye mwoyo minutes. Okay, welcome back from the short break. Can we, I'm just going into the chat. Can we have reference material, get some books used in the course of this training? Prof and Thomas, I think you've noted that. Some reference material we need to post. All right, okay, welcome back. Let's proceed now and we continue. And my own homework and try, okay, other comments will be responded to by my colleagues. Let me zoom in once again and then we continue. Okay, there we are. Like I mentioned earlier, in case you have questions or you feel something is not yet clear, post it in the Q&A. I've got this, Thomas and Susan will be willing to answer all the questions such that by the time we end the training, most of your questions are answered. So let's proceed. We broke off when we had looked at a simple logistic regression when we are considering a continuous variable. Now we are pushing on to a second one. I'm considering my other model called Logit2. Still it is simple, but this time around I'm considering a categorical variable, because the moment we understand how we interpret the results, then it will be very easy in case maybe we consider a multiple one. What happens? So again, I use the GLM. I've got the admit, that is my response variable, and then rank. This time it's categorical. Then I include in data and then the family. So I'm going to run this line. The moment I run that, and then I also, in case I run only the Logit2, like we saw earlier, what is going to happen? I type Logit, sorry, it is LG. If I type that, when I run that, what is going to happen is that in case you check in the console, what you're going to see, it brings you the formula, GLM formula, equal to that, admit, and so on. What it's giving me are only the coefficients, sorry. So I'm having my intercept at 0.164, rank 2, rank 3, rank 4. Remember, rank is a categorical variable. Last time Professor Susan was talking about how to create dummy variables. But within R, the dummy variables are created automatically. And in this particular case, we are having only rank 3, rank 2, and rank 4. Rank 1 was used at rank 1, you're not seeing rank 1. So we are using it as a reference category. K-1, what we learned. So there are 4 levels, you minus 1, implying that you're going to have 3 indicator all dummy variables. So further to that, we are having the degrees of freedom, the null diversity, the residue, and then the AIC. But what about in case I get a summary? Won't I get more results? When I run the summary, what is going to happen is that now this time around, I'm having, yes, the same thing. I'm getting the divergence residues. My formula is popped back. I've got my coefficients. I've got the estimate of the intercept. I have for rank 2, it's minus 0.75, then rank 3, then rank 4. When I look at my p-values, still they are telling me that they are significant, okay, from my p-values if I'm to consider 0.05 at 5% level of significance. So then how do I write now? How will my equation look like? So I'll write my, please look at what this equation that I have highlighted. Okay, so it's going to look like log odds, okay, of being admitted is equal to my intercept, which is 0.1643 here, minus 0.75. It's the minus 0.75 times rank 2, because this is rank 2. okay? And then minus 1.367, this is rank 3, and then minus 1.6887, rank 4. That is the equation I have highlighted. So that's how my equation will look like in case I want to write it out. And then from here, I can now start explaining my results. However, what you should note at the back of your mind that this time around, we are using rank 1 as our reference category. Within R, it is very interesting that sometimes it gives you the reference category automatically. But however, you can also command it by using the relevel command. With the relevel command, you're telling R that from the rank category, use this as my reference category, depending on what you want to discuss. Okay, so from there, for quick interpretation of our results, now I go and get the exponential. I want to get the odds ratios only for this category. I do the same what I did earlier. I run that command. So when I run, this is what I'm getting. Rank 1 is my reference category, all right? And then, so I'm having rank 2, the odds ratio is 0.47. Rank 3, I've got 0.256 if I round off. Rank 4, it is 0.18. So let me first ask in the chat, how would you interpret rank 2 in relation with having rank 1 as the reference if somebody is to be admitted? Let me hear from you. Then I also share my own way. Can you post in the chat? How can you interpret this odd ratio for rank 2? Our reference category is rank 1. Okay, let me check in there because somebody was asking, when do we use less likely, more likely? Remember what we said, that with the odds ratio, if it is less than 1, it implies that the chances of somebody being admitted in the first category, they are low, they are minimal. When it is greater, then it is more. This time around, we are comparing rank 2 to rank 1, rank 3 to rank 1, rank 4 to rank 1, because we used rank 1 as our reference category. And remember, rank 1, it's the most prestigious institution. Okay, let me check in the chat. 0.47 times less likely than rank 1, less likely, that's Stefan. Then a 50% chance of being admitted, less likely by 0.472, about 4.7 times likely to be admitted. All right, please send more comments. I'm still reading. 0.53 less likely to be admitted. Yes, because it's there is 4.7 times less likely to be admitted compared to rank 1, 47% chance of being admitted. Okay, okay, those are some of the responses that I've got. So you can say for the case of rank 1 that the odds of being admitted in rank 2 are or is 0.47 times the odds of being admitted in rank 1. In other words, the chances of a candidate be admitted in rank 2, they're 0.472 you are 0.472 less likely to be admitted to rank 1 compared to rank 2. So, by that easy way of interpretation, you can say the odds of being admitted in rank 2 are 0.47 times the odds of being admitted in rank 1. When you come to the third one, the odds of being admitted in rank 3 are 0.255 times the odds of being admitted in rank 1. When you come to rank 4, you can interpret it as the odds of being admitted in rank 4 are 0.185 times the odds of being admitted in rank 1. In other words, what we are seeing that the chances of, our reference category is rank 1, so it is rank 2 over rank 1. Or you can say rank 2 is the first group and then rank 1 is the first group, and we are comparing it to that. So we are seeing that there are 0.4 chances for you being admitted in rank 2 compared to rank 1. And then when you come to rank 3, you have 0.255 chances of being admitted in rank 3 than in rank 1. And then in rank 4, it is 0.185 chances of being admitted in rank 4 compared to rank 1. Okay, let me go back in the chart. Rank 1 is the reference category. Yes, Robert, that is true. Rank 1 is the reference category, while 2, 3, and 4 are base categories. And so we are discussing everything when we are referring to the first rank. Great. That is correct. Reference category is rank 1. So is that okay? Have we gotten how we interpret categorical variables? Rank 2 in 1 in 2, rank 2 almost 1 in 4. Okay. Okay. Or somebody can interpret it and say, the chances, well, it's the same thing that I've mentioned, that the chances of somebody being admitted in rank 2 are 0.472 times less likely to be admitted in rank 1, okay? Or the chances of being admitted in rank 3 are 0.255 times less likely to be admitted in rank 1. Why I'm using less likely? Because the OROs, the odd ratios, are less than 1. When you come to the 1 of 4, the chances of being admitted in rank 4 are 0.185 times less likely to be admitted in rank 1. Remember, these are the ranks of the institutions that we are looking at. Is this also what we can explain in the multinomial? Yes, it is the same thing we can explain in the multinomial, but with the multinomial, the levels, we are no longer using only 2 levels, we are using more than 2. For example, 3 all, 4. Okay. Is that okay? Can we continue? Type in the chat. I want to confirm it's fine. Okay. Okay. There's a question, but it has disappeared. Okay. In case we had a value that was greater than 1, our odds ratio, which was greater than 1, so we would say that you're having, for example, 1.47 times more likely to be admitted in rank 1 in rank 2 compared to rank 1. So that is how we interpret the results. Okay. What about what? Okay, there is a question that what about if admission had values 0, 1, 2, and 3? Is it still binomial? No, it is not. We said with by means 2. If you go beyond 2, that is something else. Then you shift on to multinomial, because for it, it can handle more than, it can handle 3 to 3 and above levels if you're considering a variable as a dependent one. All right, let's continue. Now, given that we've understood how you can explain a simple logistic regression with a continuous variable and then with a categorical one. So what is happening here? It is in multiple logistic regression, what what I'm doing here is that I'm considering all my independent variables in one equation. So now I call it my logit. Okay, remember the ones that the previous models that I've been looking at, it was just logit. So in this other one, I'm considering, in the last one, I'm considering my logit, which is GLM, then admit, and I'm considering the rest of I'm putting everything in one equation. Now it's no longer one equation. Then I've got my data, which is equal to graduate, and then family, it is still binomial. So when I run that, okay, and then I can ask for summary of my logit. So in this one here, when you put everything together, why I started with the simple ones, such that we are able to interpret them very well. So what we are having in this particular case again, the output has the GLM formula. I've got my GLM here. We have admit as a function of GRE, GPA, and then rank. You have to state from the start whether something is continuous or it is categorical. I come again here, considering all, I've got my estimates, all right? Then I've got my P values, and all my P values are significant for all, for all the variables. Here you're seeing only rank 2, rank 3, and rank 4, because rank 1 was used as a reference category. In like I mentioned, in R, the dummy variables are set automatically. Okay. Okay. All right. Okay, let me first finish this, then I'll post the script again. I've seen the comment. Okay, so I've put this, we are looking at the summary of what we are having. Now, again, like I mentioned earlier, it is interesting. You can be able to get the confidence intervals. What you do, you use the command confint. Most of the time you'll see that in most of the published work, apart from scholars recording the odds ratio and the p-value, they also further go ahead and record the confidence interval. So from here, I can use the confint, and then I run what is the confidence interval for my for my estimates. All right, I've got 2.5% and then 79.5%. Or I can combine everything. I can, in case I want to get the output for the exponential, I want to take the exponent and the exponent of my estimates that I got. Remember how my coefficients, I got the coefficients for my logit. I can extract them. At the same time, I want this one, if in case I put an exponent, it will give me the exponentiated values, implying that those are the odds ratio. And then this part of combining, it shouldn't confuse you. See, combine, that putting things together, only that. So I want a column with odds ratio. What am I combining? I'm combining the odds ratios and the confidence interval. This is what this line is all about. So when I run that, what happens is that this is what I get. This time around, I put everything together. I have my intercept, the odds ratio is what I'm having here. I mean, these are the results we got before, but we are just going into a step-by-step process to see how we can understand these things. And then I've got my odds ratio for the GRE as 1.01, what we had earlier. This is my confidence, and I know the p-values already because I got them. that same thing that I calculated the odds ratio for rank 2, and then the odds ratio for rank 3, and then the odds ratio for rank 4 with their respective confidence intervals. So from here, we can, now in case you want to extract information into your work or your Word document, all you need to record are the p-values and then your odds ratio, and you interpret them the way we've been explaining. Here we've put all things together. So what I'm going to do, some people are saying they're having a different R script. So what I'm going to do, I'm going to post it again in the chat. They're just simple adjustments that I've made as we are discussing. Okay. I'm going to share it in the chat. So please don't post for now. That what? I've posted in, okay. I need to select to all. Okay, please pick it. I've posted it in the chat, but it's just the same material that we sent. Okay, I have not seen it. How do you tell R, for example, to use reference 2 as a reference, not 1? We use a command relevel. You're also not seeing it? Are you seeing it? I've posted the updated logistic R. Resend, please. Okay, Prof, can you post it in the Q&A, please? Yes, please pick the updated one. Okay, I'm not posting again. I think you've gotten it. So somebody was asking, like I mentioned earlier, depending on what the relations that you want to discuss among these categories, you need to have that at the back of your mind. So you're looking, in this case, what I based on, we are looking at what are the chances of somebody being admitted in a very first prestigious institution compared for that same person being admitted to a different institution. In this particular case, there were ranks 1, 2, 3, and 4, whereby 1 is the highest and then 4 is the lowest. So still, as you're having your data, you have to have at the back of your mind that among these levels, which one do you want to discuss in relation to the other, all right? However, in case what R does, it automatically picks the first one. But in case you use the relevel command and you tell R that when you come to rank, use maybe use 2 or use 3 as my reference category. So it is very doable. You can try that in your own free time. Okay, the command is very easy. It is called relevel. You can even type, you can ask R. So when you check in my help window, what is it's saying that it reorder levels of a factor. I think we know that a factor is categorical. So what R does, the levels of a factor are reordered so that the level specific by REF is the first and others are moved downwards. So in case you want the usage, so you need to indicate that my X, you indicate the variable name, in this case, which is rank, and then you tell it that in rank, if you're seeing here that my REF, that is the reference category, so which is typically a string, so you can type it there, and R will be able to pick up what you're saying. So for example, kindly look in the help window where I am. R is giving an example of the wrap breaks and tension. This is an object. This is inbuilt data within R, okay? And the wrap break, that is my, it's the data set. So what this one is trying to say, that real level, that in the real level, this is the variable that you want to use, that within this variable tension, then don't go there, and ref is equal to, ref is reference, that I want my reference category to be this. Okay, let's do it in R. In this particular case, I can say, for example, in case I go back, if we are here, okay, we used that, I can say that I considered my data as graduate, all right? I can write that graduate, okay, then rank in that particular data, I assign it real level. So in that, I bring this one, I'm going to just copy and then I paste it. And then I say my ref, all right? Ref, I want to use rank 2. This time around, you're telling R that don't use rank 1, but use rank 2 as my reference category. You're commanding it. So you come and run this particular line. Ref not. I'll need to look at that again. Reference. Huh? Okay. You cannot. Why? Okay. Okay. I'm going to check this code again and then I'll give you an answer after that. But we use the real level command. Hmm? I need to check. I'll check that and then I'll give you feedback, maybe before we break off. Let me check it again and we can run it together. Ref must be. I'll check that. Okay, I'll check that and then I'll give you an answer later. Maybe I'm missing out something. Okay, so now that marks the end for the case of logistic regression. So in case you've got in case you've got some data that you want to do logistic regression, it's the same thing that you need. It is the same interpretation that you need to use. Why is it that the coefficient for rank 2? There is a question that why is it that the coefficients for rank 2, 3, and 4 have a negative sign? I mean, well, in this particular case, because the way you've been seeing that when you're looking at multiple regression, and some of the coefficients are negative or positive, what does it imply? It just shows an impact, whether it is a negative or positive, period. There is nothing like maybe they must be positive or they must be negative. That is the main reason as to why they are negative. So in that particular case, if you're to interpret it in terms of the multiple logistics, so it will imply that a unit increase in, you say that a unit increase in rank 2, so we'll reduce the log odds. We reduce the log odds of somebody being admitted in rank 1. Yeah, because it's negative, the negative sign you included in your explanation. But like I mentioned, it is important in case you're interpreting your results, always use the odds ratios. Well, the odds, when you take the exponent is the one that gives you the positive sign. So that should not scare you. Okay. So like we said earlier, in case you're looking at a categorical, one has to be a reference variable. For the reference variable, you're discussing you're having two groups. Your reference category is rank. So in other words, the odds ratio is equal to rank 2 over rank 1. You're discussing everything in reference to rank 1. So if our odds ratio for rank 2 is 0.472, it implies that since it's not greater than 1, so it is less likely, the chances are less likely to happen in rank 2, which is our event. So in this particular case, we can say the odds of being admitted in rank 2 is 0.472 times the odds of being admitted in rank 1. And you do the same explanation to the other ranks. Okay. So any other question? Prof, do you have more questions? More questions? So if you have questions, kindly post them in the chat. But for now, I can say that and the marginal effects, we discussed that. It's just adding them up. Okay. You have a headache. Okay, there's something I want to try. So just a second. Something. Well, in case you're having, do you keep them constant? I don't know, I'm not going to mention that. Okay. Okay, let me ask in the chat, can we continue? I'll end with okay, somebody has posted that ref is equal to 2. Interesting. Okay, let me check that before I stop sharing. I'm missing out something. Oh, yes. Yes, I think he's right. Yes, I don't know. I've not seen the name of the person who has posted. Let me check again. Wow. These things are very interesting. Okay, let me check the name again. Jericho. Wow. Okay. Hope I pronounced it very well. Thank you. Yes, there is something I was missing out. Instead of indicating 2, because in our data set 2 meant rank 2. I was recording rank 2. You're very right. Thank you so much. You see what I told you, it is always good, like you meet challenges and then see how to solve them out. Yes, in case somebody was asking, what about in case I want to reference a certain level of interest other than letting R to do it by default. So here, the command is relevel, like the way how we saw it in the help command. So this is my variable rank. Then I'm telling R that relevel, when you come to the reference, you have to always remember how your data was coded. So we coded 1, 2, 3, and 4 in our reference category. So in this particular case, when the moment you put 2, it implies that you're using rank 2 as your reference category. Now let's see what is going to happen in our result. So after running that, I come and run the second line, so that I'll have that. And then let me ask for the summary. Let's check. Now, when you look at the summary, when you look at our output in R, what it is giving us this time around is that it calls the GLM model, which is wonderful, what we've considered. But this time around, when you look at the coefficients, because you restricted it to R equals your reference to rank 2. So this time around, what you're going to have, you're going to discuss rank 1 in relation to 2, rank 3 in relation to 2, and then rank 4 in relation to rank 2. And that's why you're seeing that this time around, rank 2 is not appearing, but we are having 1, 3, and 4. Yeliko, thank you so much. That has been so good of you. Okay, great. So can we move on? That marks the end of logistic regression. I encourage you, in case you've collected some data, some surveys, and you want to apply logistic regression, please kindly go on and use it. Of course, like learning doesn't stop. We keep learning day by day, but the more you practice, the more things become familiar with you, and you'll enjoy doing your analysis. Okay, great. So can I now move on to Poisson? No. Yeah, sure. Can I move on to log linear now? The last bit of today. Can I move on to that? I want to look at log linear regression or Poisson. Kindly check the link again. I've put there some material in day 9. I'm giving you 3 minutes to download. Check in day 9. Prof, confirm for me. I've put it's going to take a very short time. I've put within day 9, I've put additional notes, SDA PDF. I've put the Gala SCSV. I've put the data set that we are going to use. Olivia is saying that it is there. If one person finds it, then it implies that, everyone should see it. Please share the link again. Then we will be using Poisson2.R. Okay, I'm giving you 3 minutes. Kindly go to the link and get to day 9 folder and get those additional materials and place them in the folder on your computer where you're working from. Okay, they have posted again the Google link. And also, don't forget to register. There is a registration link for day 9. Also, don't forget to register, and the YouTube link. Okay, I'm seeing some people are saying they are done. That is good. So can I see more? Okay, Gala SDA, yes. Done. Joel is also done. Olivia is done. Bernard is done. Esther is done. Charles, okay. Happy Banda. Is it possible to set a Google Drive folder as a working directorate? That's interesting. Prof, is it possible? Happy, you can try out. Okay, let me stop sharing this. And okay, so I'm going to use the remaining few minutes just to discuss about non-linear regression model, or call it, it is log linear, not non. Let me edit that and then we start. This is log linear. Okay, great. Please edit that, it's log linear. Okay, in the remaining few minutes, let me quickly go through this and then we continue. Okay, so like we mentioned earlier, there are many GLM models, but depends on which one do you want to relate to your data. It's quite interesting that depending on your objective, all these models can be applied. And we saw that when it will come to the GLM in R, you indicate the family that you're considering. In case you're considering a logistic regression, you'll indicate binomial. Now this time around, if we're considering a log linear regression or Poisson regression model, we'll consider Poisson. So now let's move on. It's going to be a short presentation. Just a brief introduction. A Poisson regression model is also a generalized linear model. And what this one does, it models count data, all rate data, and contingency tables. So we've just looked at contingency tables. But what is most important here is that we are looking at count data. Okay, so your Y output, which I'm calling the count, is the value that follows the Poisson distribution. All right, and in this case, it assumes that the logarithm of the expected value, that is the mean, that can be modeled into a linear form for some unknown parameters. In this particular case, the unknown parameters they are talking about, these are our independent variables. So we are going to see how do we look at that. And then also what we need to know at the back of our mind is that the response variable is in form of counts only and not fractional numbers. Okay, so most of the time when we are looking at the Poisson distribution, it's used to find the probability of events occurring within a given time interval. For example, how many, in case you're looking at number of patients that reported in the hospital, that the new patients that you received in a given day, or you can talk about a given week or a given month. We are having a time interval, or the number of accidents that were communicated in the last 6 hours of that day. Okay, and so it is important that when we are to model Poisson, the response should be non-negative with a numeric value. I've just given some examples that the counts of, for example, the counts of the number of bats, the number of wins in the football match series, among others. All right. So, so most of the time, if you're talking about counts or frequencies, and especially when your data set is very small, so we call for a Poisson distribution. And the result must be 0 or higher. So we are not going to consider, we are not looking at scenarios of having a negative number of times happening in Poisson distribution. So what we are going to do, most of the time what we do is to transform the nonlinear relationship to a linear form. And for the Poisson distribution or the log linear, the link function that is being used is the log for Poisson regression. And so that is why it is called the log linear model. That is the other name that you can use, log linear model. Among the different properties that you can dig into details or we can look at is that always the mean should be equal to the variance. And when the variance is greater than the mean, then it implies that this, we call it over dispersion. And that is, it is greater than 1. And if it is less than 1, it is called under dispersion. And all these things can easily be identified in your data as you're doing the calculation. And in case of over dispersion, what happens? We've got extension models from the log linear, for example, the quasi-Poisson and so on. But I'm not going to go into much details of that. I'm just giving you an eye opener, just in case you happen to do the analysis and you're considering a log linear model and your variance is greater than the mean. So what should come at the back of your mind is over dispersion. And in case it happens, what do you need to do? And what about in case you've got under dispersion? The extension models in the log linear models can be applied. I've already mentioned that the default link function for Poisson is log, okay? And most of the time, it is used to predict a discrete variable. We know what descriptive variables are. Like I gave an example, number of accidents, number of patients received, they have to be discrete in nature. Okay, so how does the equation look like? So with the Poisson regression equation, the general equation, it has log y, which is equal to a plus b1 x1, then plus b2 xn, and so on. Remember, on my right-hand side, these are the dependent variables, and then on my left-hand side, the log y. So now we are considering our y, the count in terms of log. So what it does, it looks at the linear, it looks at the relationship between the predictors here in this particular case and the log of the outcome, which is the count. Like here, my y is the response variable. I'm looking at it in terms of log. But remember, even from here, I can also take an exponential both sides. When I take even here, when I take exponential both sides, I can get y. Okay, so my y is the response variable. Here, a, b, b1, b2 up to bn, they are just my coefficients. X are the predictor variables. We've mentioned that predictors, explanatory, or independent variables. And still, since it is also a general linear model, we continue to use our function GLM. And so the same, we looked at in help, how do you use the GLM? You state the formula, you state your data, and then the family. The family this time is gonna be Poisson. Okay, so that marks the end. I just gave a few hints, but now let me share the slides. Let's try to see how can you come up with a log linear regression. I want to share the data set that we are going to use. Among the I'm looking at, I want to share the description of the data that we are having. Please open the description page, the Word document. Okay, let me try to delete sums. Okay. Let me try to share again. Okay, there we are. So in the data set that we are going to use, which I've already sent to you, we are going to consider this particular data set. The PowerPoint is not there. Yes. Yes. So the data set that we are going to use, it is a Gala data set. You know, R is very interesting. We have been saying that from R already has got inbuilt, it has inbuilt functions, and it's quite interesting. It also has certain data sets that you can use in case you want to practice about something before applying it on your data. So in this particular case, what we are going to have a demo on how considering the Gala data set. And this Gala data set, it is found in the far away package. So I understand you don't have this particular package. So please install it in 2 minutes. Install the far away package. We can also get more details about the Gala dataset. This Gala dataset is what we are going to use. It's an inbuilt dataset in R. So we are going to, though I extracted it for you, so I'm still going to show you how do you extract datasets in R in case you want to apply them or use them for demonstrations, or you can still use them to support you in learning how you can analyze data. So what does it entail? It pertains to the species diversity on the Galapagos Islands, okay? In this data set, there are 7 variables. So what we are going to do, we'll use Poisson regression to define the relationship between the number of plant species with other variables in the data set. Okay, so I wanted to show you briefly what the data is all about, the data set that we are going to use. This is an inbuilt data set within R, and it is found in the far away package, which I want you to install and then load. All right, if you're using the latest version, then it will be very easy for you. It will take a second. So in this case, the number of plant species is our dependent variable, and we want to see its relationship in respect to other variables. Okay, so what I'm going to do, I'm going to share with you and show you how that data looks like. Okay, then I'll show you how do we extract it in R. All right, now I'm going to stop share this, then I share my R script, and we proceed from there. For now, I'm going to close this because I don't need it. Let me clear my console. I'm going to start something new. I can as well clear my environment such that I see clearly what I'm loading. So RM list, that one clears the environment. Okay, now let's continue. Of course, we already have these packages with us. So all you need to do is to load them in the console. But I never had the package far away, which I need, but I installed it already using installed packages. So what I'm going to do now is just to load it, the library far away. Let me ask in the chat, have you been able to load the, kindly share the PowerPoint? Please check, it is It is in the day 7 folder. Prof has confirmed that it is there. Hmm? Okay, you can as well pick it in the, okay, thank you. Okay, from what I'm seeing in the chat, people are telling me the participants are telling me I've been able to load the faraway library. So the data that we want within this package, remember what we said, all these packages that you're seeing, they have got, apart from the functions, that the inbuilt functions, they also have some packages that can support you when you want to work out something. All right. So now, how do you, because the data set that I want, it's called Gala, and it's within the far away package, which I've loaded. So now what I'm going to do after uploading the far away package, I want to get the data set. So I use the command data in bracket. I put the name of the data set that I want. I use the data command, this one, and inside the data command, I put in the name of the data set that I want. Okay, so it can happen. R has many data sets. So in case you have a data set that you know that you want to use in R, all you need to do is to use the data command. So when I have that, I can come and I run R. The moment I run it, I can see, if you come and check in the environment, they're telling you that it has got 30 observations, okay? You can even click and see what is showing you that it has got species. This is just, you have species, the endemic, the area, elevation, we have the nearest, the adjacent, and so on, okay? We are going to use species, the number of species, as our dependent variable. So one thing, new thing that you're picking today, that you can extract data from R and use it in your demonstrations or to support you to understand some of this concept. And the moment you click, even the moment you click at it, we can come here and see the same. You can check in your R console. The data is, you can see it very well. For the case of the species, the endemics, the area, elevation, and so on, etc. This is the data that is being shown in the data set. All right. So sometimes you might see this data set in R and you want to pick it such that maybe you can use it next time and you don't necessarily need to extract it from R. What you can do now, this time we call it exporting data. We can export this data set from R to Excel. How do we do that? Before we were importing, getting Excel to R. Now we want to move R to Excel, our data. So we use the command called write.csv. Okay, write.csv. I want now to import this data, to export this data from R into an Excel file, such that I can use it anytime that I want. I don't need, because maybe I might forget the name and then it takes me a lot of time. So when I use write.csv, then in bracket, I start with the name of the data set, which is GAL. Then I use the argument file equal, I tell that I want this data file to be as a CSV. Okay, so when I write this particular command and I run it, the moment I run it, I don't see it here under the console. But when I go and check in the folder where the folder I'm using, where I'm storing my documents, I'll be able to see the gala.csv. Now, if you've reached at this stage, kindly go and check in the folder where you're working from and check whether you've got the gala.csv Excel file. Let me ask in the chat in case you've managed to export now. Yes, Bernard is saying yes. Okay, can I get more people? Evans, Chris, Olivier, Sharon, Stefan, great. Okay, so now in that way, can this apply to Excel as well? Yes, it can still apply to Excel. Now that you have it as a CSV, you can go to Excel and save it in with a different extension, XSLS. It does work. So now we have, first we've learned how to get data sets from R. Then how do we export data from R to Excel? All right, now let's continue. We have little time remaining. Now I'm setting my work. Now we want to, well, this is just a by the way, but in case you don't want to go into all this, since your data is already read, you can continue, or you can resume again, set the working directory, then you read it back. I mean, it doesn't matter. I only put these steps just for you to learn more, but already the data, you have the data. When you check in your environment, the data set is there. So this other one, it's the same thing that we've been doing before, but you can leave them out. We have used the command head, okay, whereby with this one, it gives you the first 6 rows of your data. You want to check how your data looks like, okay, species, endemic, the area, and so on. All right. In case you want to learn more about the data set that you've gotten from R, all you need to do is type a question mark and then the name of the data set. So this is the data set that we are using. If you type question mark girl, you type enter. You run that particular command. So when you come to the help, it will tell you that it is in the Fairway package in the R documents, and it's telling you it's dealing with species diversity on the Galapagos Islands. It is giving you the description of the data set. Remember, like I mentioned earlier, that most of the time you need to understand the description of your data set. Otherwise, it will be hard for you to see the relationship that exists in the variables that you want to consider. So it is giving you the description, and it is looking at the relationship between the number of plant species and several geographic variables is of interest. So you can continue and read further. They will tell you usage, that is data. They explain to you the different variables, what they mean, endemics, that is the number of the endemic species, then area, the area of the island, the elevation, the highest. I mean, yes, it is telling you what the nearest, the distance from the nearest island, the adjacent, the area, and so on. And that is the source. That is the package that we want to use. You can talk about the summary. So we've seen that. You can ask about the summary in case you want to have a quick look. So it will give you the different summary. For example, it will tell you the area, the elevation, the nearest, the number of species that we are having. It will tell you the minimum, the mean, and so on, because of all these ones are not. So our counts are the species, 1, 2, 3, and so on. Okay, now we know how to use the summary command. So we are going to proceed, and I'm going to skip because some of the things, but you can do them in your free time. You can try to generate a histogram for a species in order to check if the variable follows a log linear relationship or a Poisson distribution. I used the histogram from my data set girl, pick for me that species. The size of the bins, let them be 10. The X level, that is X label my X axis as species count. Main means the title, that is my title, and the distribution of the species, and then prob is equal to true. So in case I run this, I know it's going to give me an error. Yes, that the figure margin is too large because this place is very small. But in case I zoom out, then I'll be able to see how my histogram will look like. Okay, if you want to try again, let's see if the error will, let me run again and see if the space is enough. Still the same thing, I need to zoom out. Let me try to reduce and run again. In case I run again, it has moved to a different line. I wanted the histogram first. I can run now. You can see my histogram, the species count, and then my title as the distribution of the frequency, and the distribution of the species, and then the frequency. All right. I can as well go ahead to generate a box plot to get more insight in the distribution of the pattern. And we've learned how you can zoom out and see how the box plot of the species. So now what I'm interested in most is my main interest is how do I create a Poisson model. Remember what we said, we are going to use the GLM. Okay, we are still using the GLM. My species is the count. Okay, my dependent variable, it's a count, the number of the species, and then the independent variables are the ones that are put there. Then I comment about the data that I want, that pick my data. I called it girl, and then this time around the family is what? Is Poisson. So you can run your object fit, and then you can run. So in that particular case, remember you have to indicate your family that it's Poisson, and then so in case I run that, let me zoom in such that they come more. All right. So in case I run this line here, the GLM, and now I run summary fit. What is happening? Okay, so in case I run the results that I'm getting, if you check very well, I've gotten my GLM species, and then in relation to the other dependent variables, my family is Poisson, and then my data is Gala. So it is quite interesting is that basing on the analysis that we are seeing, we have the intercept, the endemic is I mean, when you look at the p-values, what we are having, that endemic area, they have got the p-values that are less than 0.05, and then the nearest is less than 0.05. So most of the time as we are doing the analysis, you can say, well, I'm going to move on and reduce my model and only include the variables with variables that are significant. So it is what I did next. I removed all the other variables that were not significant and only considered 3 variables. It is still the same thing, only that this time around, in this one, which I called fit.reduced, I only considered the from the full model, I only considered 3 variables that were significant. And I did the same thing. So in case I'm to run that, okay, and then I call for summary. So when I check again and I see my result, still in this particular case, the output produces divergency, the regression parameters, the standard error. And we can see that now this time around, all the variables that I'm considering are significant. Okay. Still, now we need to move on how do we interpret the results. So within when it comes to log linear regression, or call it the Poisson. Remember, our dependent variable is modeled as a log of a condition mean. Looking at the estimates, the regression parameters that we are having, for example, when you look at the endemics, it is 3.551 e to the power 0.3, which is 0 to the power 2. So which is 0.0, yes, 0.03551. Okay, that so you can say that when you check in the script, I've tried to put some explanations that in that particular case, the regression parameter of 0.0355 for the endemics. So it indicates that a 1 unit increase in the variable is associated with 0.04. I've rounded off from 0.0355, I've rounded off to 0.04 increase in the log mean number of species holding other factors constant. So in case we are to look at this variable, the estimate for the endemic, so which is 3.551 e to the power negative 0.2, which is the same as 0.0355, or you can round it to 0.4. You can say that a unit increase in the endemic variable is associated with a 0.04 increase in the log mean number of species holding other factors constant. And the same story you can do the same for earlier, and you can do the same for the nearest. So, but what is interesting is that when you check in that particular folder, there is a document which I put there, which is called additional notes _SDA. When you open that PDF, it has got a very detailed explanation on how you can go about explaining or interpreting the results that you're getting from when using a log linear regression model. It is 2:02, so I'm going to stop here unless if there is a burning question, then we can respond to it. I kindly encourage you to go in the R script Poison 2 and go through slowly by slowly. I've also put where you see the comments, those are just explanations that can help you on how you can go about when you're explaining when you're interpreting the different result. And also the additional notes in the DEN 9 folder will help you to understand more what is all about with the log linear regression models. I'll end here for today. Thank you so much for being patient, and hopefully you've learned a lot. Stanley is saying that can we have a recap for tomorrow with Poison? If Professor Susan allows me, I'll do a recap because she's the one that is going to come in. So, which dates? Okay, thank you so much. It has been a wonderful time to share with you, and let's keep it up. Thanks for being patient. We are still pushing on up to Saturday. Since we've been able to persist, why not? Let's continue till the end. People are asking about certificates. Yes, certificates will be given according to attendance. And Dr. Thomas is the one in charge. So if he doesn't, so please, let's continue and keep the spirit even in the remaining days. Otherwise, if you don't register, they will not send you a certificate. Thank you once again. Have a great time. Yes, I gave. Kindly do the assignments and then you'll share tomorrow. Okay, bye-bye. Have a good afternoon. Thank you all, bye-bye.
We are done?
Yes, thank you, we are.
Okay, thank you.